Hello everyone, I hope you all are doing well. Today we are doing 9701 May-June 2017, paper 1-3, chemistry. So let's start. Question number 1. The ion Y3 minus contains 18 electrons and has a mass number of 31. How many protons and neutrons does Y3 minus contain? So if it's 3 minus and it has 18 electrons, that means it has an overall negative charge, right? So there are more electrons than protons. And if it's a 3 minus charge, that means there are 3 more electrons than protons. So if there are 18 electrons, then there must be 18 minus 3, which is 15 protons, right? So it's either A or B because the charge is 3 minus, and then because it has a mass number of 31, so your number of neutrons would be 31 minus 15, because mass number is basically the number of neutrons plus protons in the nucleus, right? So um, it would be 31 minus 15, so that will just be 16, and so our answer will be A. Okay, next. A 0.216 gram sample of an aluminum compound reacts with an excess of water to produce a single hydrocarbon gas. This gas burns completely in O2 to form H2O and CO2 only. The volume of CO2 at room temperature and pressure is 108 cubic centimeters. What is the formula of X? Okay, so we know that it has aluminum and carbon only, right? And let's think about this. So, well, if we have a single hydrocarbon gas produced when the aluminum compound reacts with an excess of water, then we can assume it's just CXHY, right? Because it's a hydrocarbon, so it must have hydrogen and carbon only. So we can assume the number of carbon atoms is X, the number of hydrogen atoms is Y. You can assume that. And then they are burning that in oxygen, so it's combusting it, and it forms H2O and CO2 only, right? And then the volume of carbon dioxide at room temperature and pressure is 108 cubic centimeters. So volume is 108 cubic centimeters. And if we want to find the moles of carbon dioxide, then we know the formula that moles equals the volume over 24 at room temperature and pressure. I mean, so that would just be, it's this is 24 dm cube, right? So if we need to convert 108 cubic centimeters to cubic decimeters, then we just divide by 1000. So 108, so n equals to 108 divided by 1000 basically over 24, right? So if you do that, it's 0.108 over 24. So you get 4.5 into 10 to the power of minus 3, or you could write it as 0.0045 moles, right? So that's the moles of carbon dioxide that you have, that will just write on the top, okay? And now, if you have this many moles of carbon dioxide, now let me just actually balance this equation first before I do anything. So Cx, right? That means over here, if I have carbon dioxide, the coefficient here would be, the stoichiometric coefficient would be x, because I have x carbon atoms. And then H is, there are y atoms of hydrogen, right? So this would be y by 2 because I have H2O, right? And let me make this better a bit. Okay. And I'm not really balancing oxygen right now because that would take too much time. But not too much time, but it's not important for this question. I mean, but if you want, you could just y by 2 plus 2x. So, and then you divide that by 2 because it's O2, right? So yeah. And what was I doing? I lost track. Yeah, okay. So I am we know this, that this is 0.0045 moles, right? And so what we can do is consider this equation, CXH5 plus O2 gives you y by 2H2O plus XCO2. I'm not writing the coefficient over here. You would, for each situation. So if you have Al2C3, that means that it is C3Hy plus O2 and whatever, right? I'm not writing the coefficient for O2. I already told you that, but if you want, you could. just to be more algebraically and chemically correct. But C3Hy, right? Because you have three carbon atoms in Al2C3. So you have C3Hy and you would have three CO2 here, right? And basically your X is 3. So if you have 3 CO2, obviously we already know this. This is information that we already know, that is 0.0045 moles of carbon dioxide. So if you have 0.0045 moles of carbon dioxide, that means how many moles of this hydrocarbon do you have? CXHY, right? C3Hy, I mean. So that would be 0.0045 divided by 3, which would be 1.5 into 10 to the power of minus 3, or you could write it as 0.0015 moles, right? So I have 0.0015 moles of this. Now my second step, so that's my first thing that I've gotten, right? Which is that this is 0.0015 moles. The second step to this process is that you have Al2C3, and you know that you have 0.216 gram sample of the aluminum compound X. So if you assume that X is Al2C3, then what will be the molar mass firstly? Use your periodic table. So aluminium, it has a molar mass of 27. So 27.0 into 2, because you have two atoms of aluminium. And then because you have three atoms of carbon, so that will be 12.0 times 3. Okay. And so how much will that be? That will be 90. It's 90.0 grams per mole, right? That's the MR of Al2C3. So now you just calculate how many moles of Al2C3 you had initially. I mean, before you reacted it and before the hydrocarbon burnt and all that stuff. So N equals M over Mr, mass over molar mass is the moles, and mass is 0.216 grams, right? Which is a set constant as well, because they've mentioned in the question, divided by 90.0, and so you get 0.216 divided by 90. That is 2.4 into 10 to the power of negative 3, or 0.0024 moles, right? So now you just see, because basically the thing is that because this is C3, Al2C3, right? And this is C3Hy. So basically the ratio of Al2C3 to C3Hy is 1:1. So the number of moles of Al2C3 I have should be equal to the number of moles of C3Hy I have. Now, for the first option, which is Al2C3, I got the moles of C3Hy as 0.0015, and I got the moles of Al2C3 as 0.0024, which is not a match, is it? So that means the first option must be wrong, okay? And now I will do the same process for the other options, okay? So I will continue this process for the other options. I hope you understand it, however. Okay, so now for the second option, I have Al3C2. So firstly, let me just calculate the MR. So 27.0 times 3 this time. And you have two carbon atoms, so 12.0 times 2, right? So how much does that come out to be? 27 times 3 and plus 24, so that's going to be 105 grams per mole is the molar mass. Okay, so now if I calculate the moles of Al3C2, I'm doing the second one now, B, I mean, so that will be 0.216 over 105. 0.216 over 105 is 2.0571 into 10 to the power of negative 3. Okay, moles, or you could write it as 0.0025 2057, sorry, 1 into whatever, sorry, into nothing actually, 0.002057 1 moles. Anyways, the point is that that's the number of moles of Al3C2 I have. And then if I consider this in this equation, I have two atoms of carbon per Al3C2 molecule, right? Two atoms of carbon, which means now this will be 2 CO2 in my equation. So X is equal to 2. So it's C2Hy, right? And now, because of that, the ratio is 1:2. So I will make 0.0045 divided by 2 to find how much CXHY is. And that will be 2.25 into 10 to the power of negative 3 moles. Now just check, is 2.25 into 10 to the power of negative 3 equal to 2.0571 into 10 to the power of negative 3? No, it is not. Obviously, there could be a chance that none of these answers will match perfectly. Then in that case, you would consider the option that is closest. But let's anyways check option C. Al3C4. So that means now I have 4 carbon atoms per the Al3C4 molecule. So I will make the ratio as 4:1. All right. It's 4 CO2 now to C4Hy. So 4:1 now. And so I'll make 0.0045 divided by 4 to find how many moles of CXHY I have. And that's 1.125 into 10 to the power of -3. All right. And next, what I'll do is my MR, I'll have to find the MR of Al3C4. So I have 3 aluminium atoms and 4 carbon atoms. So I will change this a bit. So 27 times 3 is 81 plus 48. That is going to be 129. So the MR of Al3C4 is 129 grams per mole. Now the moles of Al3C4 will be 0.216 over 129. So 0.216 over 129 will be 1.6744 into 10 to the power of -3 moles, which is definitely not a match. So I will cancel option C as well, which obviously just leaves option D as the correct answer. But you know, best to check. So we shall check. So in option D, you have Al4C3. So you have 3 carbon atoms per the every molecule of Al4C3, C3, sorry, and therefore your hydrocarbon will be C3Hy, and this will be 3 moles of carbon dioxide formed. So per every mole of this that combust, a molecule of this that combust, or whatever mole. Okay, anyways, point is the ratio is 3:1, 0.0045 divided by 3, and that will be 1.5 into 10 to the power of -3 moles. All right. Now you will calculate the MR of Al4C3, which is 27.0 times 4, and then 12 times, 12 times 3. So that will be 144 grams per mole. So then you just take 0.216 over 144. 0.216 over 144 is going to be, look at that. Option D did turn out to be the correct answer because the thing I'm getting on my calculator is 1.5 into 10 to the power of -3 moles. All right. Maybe I should write moles a bit ahead, up, or whatever. If you see here, the moles of C3Hy that I got is the same as the moles of Al4C3 I got, right? And it should be because over here I have Al4C3 and over here I have C3Hy, right? So that means, that implies that option D is the correct one. So yeah, I hope that all made sense. It was quite a very calculation based question. Next question. Which equation correctly describes the complete combustion of an alkene CnH2n? Alright, so you have CnH2n. Okay, so let's see which one is balanced, I suppose. CnH2n. Here you have NCO2, so N is balanced. Sorry, C is balanced, I mean. And then H2n, right? H2n. And over here you have 2NH2O, which means that the number of H atoms you have is 2n times 2, which is 4n, which is wrong because if you look at the reactant side, your number of H atoms is just 2n. So on the product side, however, it is 4n, which means that equation A must be wrong. All right, now if you look at B, you have CnH2n by plus. Okay, so let's see, Cn and C, so that is balanced. Now H2n, and over here you have H equals to 2 into n, which is basically 2n. So H is balanced as well. Now let's look at the oxygens. So oxygens, here we have 3 by 2 NO2. So on the reactant side, your oxygen equals to 3 by 2 N into 2. So that is basically 3N, right? So that's not a zero, that's oxygen, by the way. I know it looks like a zero. I don't know why. Anyways, that's on the reactant side. On the product side, you have O equals to 2 into N. So 2 into N is 2N plus on over here you have 1n, right? So n. So 2n plus n is obviously 3n. So 3n and 3n. So carbon is balanced, hydrogen is balanced, oxygen is balanced. It seems that B is the correct answer. And obviously you could use the same method to test out you know, uh, C and D as well. Yeah. Question number 4. Two conversions are shown. So ammonium ion is converting to ammonia, and then you have ethene converting to ethane. All right. Which similar feature do these two conversions have? Change in oxidation state of an element. Well, hydrogen, I would assume it to have a fixed oxidation state of +1. So if I check NH4 plus, I have +1 times 4, +1 times 4 because I have 4 hydrogens, and plus now nitrogen, I don't know its oxidation state right now, so I'm just going to take it as X. And the overall oxidation state of this ion is +1. So +1 times 4 plus X equals +1. Now X equals to +1 minus 4. X equals to -3, right? -3 or -3. So that means that over here, nitrogen has an oxidation state of -3. Let's check NH3. Again, hydrogen, it will have a fixed oxidation state of +1. So +1 times 3 because I have 3 hydrogen atoms, plus X, let me take nitrogen as X, and then that equals to 0 because it's a ammonia. So ammonia, it's a compound that has no charge and stuff. So yeah, now X equals to now just make that to be like so it becomes -3. X equals to -3. So A must be wrong then, obviously, because my hydrogen, I told you, it has a fixed oxidation state of +1, and nitrogen, on the other hand, in both of them I checked, and it is -3. So that means that there is not, like, both these conversions definitely, like, I mean, I didn't check the second one, but from the first one already I can tell that it doesn't change in oxidation state. So that means which similar feature do these two conversions have? Both of them should have it, so A is definitely wrong. Now the second option is decrease in bond angle. So let's determine the bond angles. So firstly I have NH4 plus, right? So let us draw it out. Oh, okay, N, and then we have H. I'm drawing out ammonium ion. So NH, H, 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 right? And then plus. So over here, how many because the steric number, which is steric number is basically the number of total number of lone pairs and what do you call it, lone pairs and sigma bonds that for the central atom, right? So N, and that's how I'm going to calculate the bond angle. So over here in ammonium, actually, one of the, like, nitrogen has 5 valence electrons, right? So one is over here, obviously, one electron, then the second one like this, and the third one like this. Obviously hydrogen has just one valence electron, and then the one the 1, 2, 3, so fourth and fifth one, they are donated to the hydrogen. So this is a dative covalent bond or a coordinate covalent bond, and that this was actually initially H plus, and now when it reacted with NH3, it became NH4 plus, as you can see, NH4 plus. So that is how the ammonia ion is formed, and that shows because NH3 plus H plus gives you NH4 plus. That shows you because that ammonia is accepting a proton, right? It's a proton acceptor, so it's a base that proves it. So, anyways, the point actually is that the steric number, because I have 1, 2, 3, 4 sigma bonds, 4 sigma bonds and 0 lone pairs, because this lone pair actually got donated to the hydrogen. It's when a coordinate covalent bond. So if there are 4 sigma bonds plus 0 lone pairs, that means my steric number is 5. Oh, sorry, it's what? I don't know how that math is mathing. It's not actually, but 4 plus 0 is obviously 4. All right, 4 plus 0 is 4, and so that means if my steric number is 4, that means that my hybridization will be sp3. So sp3. So because 1 plus 3 is 4, right? So sp3. S and P3, sp3, then what does that imply? Because there are no lone pairs, that means that because every lone pair reduces the bond angle by around 2.5 degrees. If there are no lone pairs, that means that if it's just sp3 and no lone pairs, so 4 bond pairs and zero lone pairs, right? That's what I'm trying to say. Then that means, according to Vesper theory, that my shape is going to be tetrahedral. Tetrahedral, if it's tetrahedral, then obviously my bond angles are going to be 109.5 degrees. So NH4 plus has a bond angle of 109.5 degrees. So each of these angles, the H and H bond angles are 109.5 degrees. I hope that makes sense. Now we shall go to NH3. NH3 is different, right? Because obviously there's three hydrogen atoms like N, and then you have H, 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 right? And there's one lone pair. So one, two, three, and then four, five. So that's how the five atoms of nitrogen are arranged. So obviously you have one, two, three sigma bonds and one lone pair. So three plus one equals four. So your steric number is four. So you have three bond pairs, one lone pair, which implies that obviously because again it's still four, so your still your hybridization will be sp3, but because there's one lone pair, so the bond angle will not be 109.5 degrees, it will be reduced by 2.5 degrees approximately. So that becomes 107 degrees approximately. So 107 degrees is the HNH bond angle in ammonia. I'm writing HNH, I should write 107. And this shape, the shape of ammonia, which has 107 degrees, is called a pyramidal shape. And it's similar like NH3, NCl3, PH3, PCl3. These are some more compounds that have, this structure, pyramidal. And then we have C2H4, which is a symmetrical molecule, conveniently enough. So C double bond C, H ethene, H, right? And then over here, because pi bonds are not counted in the hybridization and all that, right? So over here, by my darkening these, I'm sorry, I might add to confusion actually, but I have one. So you can consider any of these carbon atoms because it's a symmetrical molecule, right? So I'll just consider this one. So we have one, two, three sigma bonds, okay, and this is a pi bond, so I won't count it. One, two, three sigma bonds. And how many lone pairs do I have? Well, carbon has four valence electrons, and all of them are used in the bonding, so there are no lone pairs. So that means three lone pairs that are for sigma, and zero, sorry, three bond pairs, sorry, that are for sigma, and zero lone pairs, right? So 3 plus 0 equals 3. So obviously then it's because it's 3, the steric number is 3. So it's going to be sp2, right? So sp2. sp2 implies that the bond angle will be 120 degrees, which means the shape is trigonal planar. And because there are no lone pairs, that means the bond angle will not reduce. It is 120 degrees, okay? This is 120 degrees. If you look at C2H6, just draw it out. Yeah, so C2H6 is ethane. Yeah, okay. So that is ethane. And again, it's a symmetrical molecule, so you can consider any of the carbons. Just for fun, I'll take this one this time. Now, how many sigma bonds are there? One, two, three, four. Um, So that means if there are four sigma bonds, then firstly I have four bond pairs, and then lone pairs, because carbon has four valence electrons, all of them are used in bonding, so there are zero lone pairs. And so my steric number, which is the number of which is the number of sigma bonds plus lone pairs, is four. So therefore, because it's four, I'm going to have sp3 hybridization, and because there are no lone pairs, my bond angle will be 109.5 degrees, and it will be a yeah, I forgot the name. It will be a tetrahedral. Why did I forget that? I don't know. But 109.5 degrees tetrahedral, and it'll not decrease because there are no lone pairs. And this will be 109.5 degrees. And now we shall see if this is actually a decrease. So 109.5 degrees to 107 degrees is a decrease. Then 120 degrees to 109.5 degrees is a decrease. Decrease. Again, I hope we're not getting confused between degrees and decrease. I don't know if my accent makes it clear or not, but anyways, that's not the point. Decrease in bond angle is definitely shown in both of them. So I would say that B is the answer. But let's look at C and D as well. Oh, what happened? Okay, let's look at C and D as well. Formation of a lone pair of electrons. Well, in NH4 plus to NH3, yes, because if you remember the way I drew, I'm not drawing it. Okay, let me just draw it exactly. So H, 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 H. And this one's going like this, and this is plus, right? So the lone pair was like this, and then in NH3, you just have a lone pair. So for NH4 plus to NH3 is definitely true that a lone pair is formed. But if you look at C2H4 to C2H6, there's no lone pair that's formed. Actually, it's just that the double bond breaks and one single bond is added to each one, right? So, I mean to say, even here carbon forms four bonds, here carbon forms four bonds, and in ethane as well, carbon forms four bonds, right? So there's no formation of a lone pair of electrons in the conversion of ethene to ethane. Now, if you consider loss of a pi bond, loss of a pi bond definitely does take place in ethene to ethane, as I just showed you this, because this is a sigma bond. Like I mean, it's not necessary that the top one or bottom one is the sigma bond or pi bond, but my point is the first bond that is formed between the two atoms is sigma, and the second one will be pi. And if there's a third bond, a triple bond, I mean, then it will also be pi. Sigma and then pi and then pi. So that's my point. So there's a pi bond here. If there's a double bond, that implies it's a pi bond, and then over here you just have single bonds, so it's all sigma. So that means there is a loss of a pi bond here, but in NH4 plus to NH3 there is no loss of a pi bond, is there? So that means that D is wrong as well. So B must be the correct answer. All right, next question. All gases listed are at the same pressure. Which gas will most likely approach ideal behavior? Okay, so they're using ammonia and neon, and they are comparing temperatures as well. So if I look at ammonia, I keep drawing this like this, but anyways, whatever. So I have NH, and then this lone pair, right? That's ammonia. And then I have neon, which is just neon. So obviously, one of the laws of ideal gases is that they have the assumptions, I mean, is that they have no intermolecular forces of attraction, or very insignificant intermolecular forces of attraction, right? So obviously neon being an not an ideal gas, sorry, being a noble gas, right? It's a noble gas, and because of that, it's a monatomic gas. They're very, very insignificant van der Waals forces, or you could say very, very insignificant temporary dipole-induced dipole forces between the neon atoms, because it's a noble gas. So definitely I would say that I can cross out ammonia, because definitely neon has much, much, much weaker intermolecular forces if you consider NH3. NH3, it has a hydrogen bonding as its most significant intermolecular force. Obviously, if you have if I have a stronger intermolecular force like hydrogen bonding, you still have the weaker ones like permanent dipole and permanent dipole, temporary dipole, right? But my point is that it has hydrogen bonding, and which elements have hydrogen bonding is when the three most electronegative elements. So the five most electronegative elements are fluorine, oxygen, nitrogen, chlorine, and bromine. Now, hydrogen bonding is when hydrogen is bonded to either fluorine, oxygen, or nitrogen. Like the three most electronegative elements are bonded to hydrogen in a compound, then you would have hydrogen bonding. So in ammonia, you can see that's the case because you have the N bonded to H, right? So there's definitely hydrogen bonding, which is a which is the strongest intermolecular force out of uh, temporary dipole, induced dipole, and permanent dipole forces, and hydrogen bonding. So out of these three, hydrogen bonding is obviously the strongest. So that means that ammonia is much less ideal than neon, because an assumption of ideal gases is that the molecules of an ideal gas have um, no or very insignificant intermolecular attractive forces, right? So then my correct option would be either C or D. And the second thing to consider is neon at 100 kelvins or 500 kelvins. So if the like if I have a smaller volume, so imagine this circle represents a volume. I know it's not a perfect circle, but whatever. And this is a larger volume, right? So this is small volume, okay, and this is a large volume, right? Or larger, I should say, but anyways, volume. And basically, if I have a larger volume and the same number of particles, then the gas particles have more space to move, right? So they'll be further apart, and because of that, the intermolecular forces of attraction between them will be weaker because they are spread further apart if you have a larger volume. So if you have a larger volume, your gas is more ideal, is what I'm trying to say. And now there's a law, Charles' law, which says that volume is directly proportional to temperature, right? The change in volume is directly proportional to change in temperature for a system which has fixed pressure and fixed number of moles of gas, right? So what that means is that if the temperature increases, assuming that my pressure, and it does say that at the same pressure, so that means pressure is constant, and I'm assuming that the moles of the gas will be all constant as well. So if my temperature increases, then my volume will also increase according to Charles' law. V is directly proportional to T, right? So if my temperature increases, then my volume increases, and if I have a larger volume, then my gas particles will be spread further apart. So there will be weaker and weaker forces of intermolecular forces of attraction. So the gas will be more ideal if the volume is larger. So that means the gas is basically uh, more ideal if the temperature is higher. Because if the temperature is higher, the volume will be greater, right? So that means I can cancel out, like if I'm comparing 100 and 500, 100 will be less. 500 is the greater temperature, which means that neon, the gas would have more volume. And so because of that, uh, you know, it's more ideal. So neon at 500 kelvins would be the correct answer out of A, B, C, and D. I hope that makes sense. Now the next question. The following data are needed for this question. So they've given these enthalpy changes of formation. Carbon monoxide reacts with iron 3 oxide. And what is the enthalpy change when 55.8 grams of iron are produced with this reaction? Okay, so if you check the periodic table, so 55.8 grams they've mentioned, right? So actually the molar mass of iron is 55.8 grams per mole. So what they mean by 55.8 grams of iron is actually just 1 mole of Fe, 1 mole of iron. They're just saying it in a convoluted way to confuse you. All right, that's all. And yeah, so we just need to make a Hess cycle for this, so I just make a Hess cycle. Actually, I'm like a different color now. So 3CO gaseous plus, I'm just rewriting this basically. Fe2 is to make it clearer for myself. Gives you 3CO2 gaseous plus 2 Fe solid, right? And then you have over in the bottom, you have 3C, because if you see here, I have three atoms of carbon here, 3 atoms of carbon here, so I'm taking a 3C solid. I'm going to make formation arrows upwards, by the way, if you can see what I'm doing. And how many iron atoms do I have? 2Fe, 2Fe, right? So 2Fe solid, and oxygen. How much oxygen do I have? How many moles of oxygen gas would I have produced from this? So 3 plus 3, that's 6. So 6 means 6 by 2, which is 302. 3 twos are 6, right? And yeah, even in this side 3 twos are 6. So this balances out, and now we're going to make upwards. That was not a beautiful arrow, I will admit, but upwards arrows, okay? And now we shall fill out this table. Not the table, I mean to say the cycle. So I have enthalpy change of formation of carbon monoxide as minus 111. So carbon monoxide, I have 3 moles of carbon monoxide being formed. So that will be minus 111 times 3. And then I have Fe2O3. Enthalpy change of formation of Fe2O3 is minus 822. And I have 1 mole of that form, so negative 822. Okay. And then carbon dioxide, and which is the formation of carbon dioxide, is minus 394. So negative 394 times 3. All right. Times 3 because I have 3 moles of carbon dioxide. And obviously, I started with 2Fe solid and I can't form 2Fe solid from 2Fe solid because you can't form an element in its standard state from an element in the standard state. That basically means that the enthalpy change of formation is 0, right? Is my point. So then this part is filled, but then what is left is that how many, um, what do you call it? Enthalpy change when 55.8 grams of iron. So over here, this is for 2 moles, but later I have to change it. But let me take this as X for now. Okay, I'll show you what I'm trying to say later. But basically, let me erase some of the top stuff actually. Yeah, okay. And now my point is, okay, so this is a Hess cycle. So this is my route 1, and using the same starting point and the same ending point, but a different route, I have my route 2. All right, this is my route 2. So now I have to put both these routes equal to each other. So route 1 is that, and I will just write it above, right? So x, which is my route 1, x equals to, over here I'm going against the direction of the arrow, right? So I will put a negative sign, and then minus 111 times 3, if you calculate that out, minus 111 times 3 is just 333, obviously. Yeah, and then minus 822 you have. Okay, but I'm putting a negative sign on this calculation because I'm going opposite the direction of the arrow against the direction of the arrow. And over here I'm going with the direction of the arrow, so I'll just put a plus sign, okay? And this will be minus 394 times 3, which is 1182. So this will be minus, I'm not changing this sign, I am changing the sign of the, because it's originally supposed to be plus. So I'm not changing this because, over here, against the direction of the arrow, so on this calculation, overall I put a minus sign, but over here I'm not, I'm going with the direction of the arrow, so I did not put a minus sign, I put a plus sign as normal. So minus, anyways, 394 times 3 is 1182, so minus 1182. And then if I calculate this out, what do I get? Minus 333 minus 822, you get minus 1155, and make that minus answer. So then you make that 1182. Okay, so I got the answer as minus 27.0 kilojoules, right? Per mole, technically, but the thing actually that I don't want to write per mole is that this is for 2 Fe, right? And they asked me about 1 mole of Fe. So the actual answer would actually be, because they have asked me about 1 mole of Fe, whereas this equation that they've given me is for 2 moles of Fe, if you're getting what I'm trying to say. So this, the actual answer equals to minus 27.0 divided by 2. So minus 27 divided by 2 would actually be minus 13.5 kilojoules per mole. Does that, I hope that makes sense. And so therefore your answer is going to be B. All right. And yeah, next question. Vanadium reacts with dilute sulfuric acid to form V2SO4 thrice and hydrogen gas. What happens to vanadium atoms in this reaction? All right. So let us write the equation, shall we? So it's vanadium that's reacting. So I have V2, right? So I'll just assume that this is 2V plus H2SO4. And because it's SO4 thrice, I'm going to assume this is 3H2SO4. And this is reacting to give me V2, SO4 thrice, and hydrogen gas. That will be 3H2, 3H2SO4, so 3H2. And now, what happens to the vanadium atoms in this reaction? So over here, in the pure, to say in the natural state of vanadium, which is just V, not in a compound, so that'll obviously its oxidation state will be 0 in that, in this elemental state. And then over here in V2 SO4 thrice, SO4 is that ion has 2 minus charge, so it's SO4 2 minus, right? So if I have 3 of SO4 2 minus, that means my charge because of this is 3 times minus 2, so that'll be minus 6. So if this is minus 6, then let me just take the oxidation state of vanadium as X, but I have 2 atoms of vanadium in V2SO4 thrice, which will be 2X. And the overall charge of the compound is 0, right? So V2SO4 thrice, it's the overall charge is 0 of the compound. So 2X equals to plus 6, X equals to plus 3, right? So over here, my vanadium has an oxidation state of plus 3, okay? And yeah, so now let me see what is happening to the vanadium atoms, because what is happening is basically that um, because each one is getting plus 3, so each one is so basically we know the oxidation is loss, right, and reduction is gain. So oxidation is loss of electrons, so if it's going from 0 to plus 3, it is becoming oxidized because its oxidation state is increasing. And that means that if it's becoming oxidized, that means it's losing electrons, right? So oxidation is loss. So we're saying all of these say they lose 3 electrons, but oxidation is lost, right? And some of them say reduced. I'll cancel B and D because they say and are reduced, but the vanadium atoms are obviously, because the oxidation state is increasing, they're being oxidized. Okay. Second, secondly, it's basically SO4 2 minus. I already told you it's 2 minus, right? And because there are 3 SO4 2 minuses, so it's going to be 2 minus times 3, so that's going to be minus 6. If this is minus 6, That means V2 overall should also be plus 6, right? It's charged. But because there are two vanadium atoms, that means each one has a plus 3 charge. V plus 3 and V plus 3, or you could write it as V3 plus whatever you want to do. But anyways, my point is that each of them is losing 3 electrons to cause an overall loss of 6 electrons from the two vanadium atoms, and the SO4 2 minus gains the six electrons. So overall, this is like neutral, or not neutral, but uncharged. Yeah, that's what I mean. Anyways, same thing. But they lose 2 electrons. This is wrong. They lose 3 electrons, as I showed you. 0 to plus 3 is plus 3, right? So losing 3 electrons because oxidation is happening and it's oxidation is lost. That means that the correct answer will be they lose 3 electrons and are oxidized, right? So that's option A. Okay, now we go to the next question, which is question number 8. Na2S2O3 reacts with HCl as shown. When calculating the oxidation number of sulfur in Na2S2O3, the average oxidation number of the two sulfur atoms should be found. I don't really know why they mentioned this, because isn't that what we always do, kind of? Anyways, let's leave that. Let's focus on the question. What is the oxidation number? I don't know if I'm wrong. Correct me in the comments. What is the oxidation number of sulfur in each of Na2S2O3, SO2, and S? Okay, so in S it's the easiest because that's a pure elemental form, so it's going to be 0. Done. So it's either B, C, or D. We can cancel out option A already. If you look at SO2, so SO2 oxygen has a fixed oxidation state of -2 usually, and there are two oxygen atoms, so it will be -2 times 2. Let's assume that sulfur has an oxidation state of X, and overall the charge of SO2 is 0, so then that means that the overall oxidation state is 0. So X equals to -2 times 2 -4, so X equals to, if you do the other side, it becomes +4. So X equals to +4. So over here, sulfur is +4. Okay. Now, if sulfur is +4, what does that mean for us? Again, B, C, and D are correct, but again, A is cancelled out, so we can, we're definitely sure that A is wrong. But now let's look at Na2S2O3. So this is just, a fun fact that you should know, that S2O3, this complex ion, its charge is 2 minus. So S2O3 2 minus. So I already know this. I'm not going to use Na2. If you want, you could do that as well. Like you could just consider that I'm using this whole compound, or group 1 usually has a fixed oxidation state of +1. So this is one method you could do it, +1 times 2, because there are two sodium atoms. And then you could assume that sulfur is just X. So then 2X, because you have two atoms of sulfur, and then plus and minus, actually, because -2, because that's the oxidation state of oxygen, and then 3 oxygen atoms, so that will be times 3 equals to 0, because that's the overall charge of the compound. And so 2x minus 6 plus 2, so -6 plus 2 becomes -4 equals to 0. 2x equals to +4, x is equals to +2. So this shows that the oxidation state of sulfur is +2. So it's either A or B, but I already cancelled out A from these two. So the one that has all ticks is B. So B is my correct answer. The other method is S2O3 2 minus. I told you it has a 2 minus charge. And like you have 2 Na plus, and you have S2O3 2 minus. That's why it's an overall neutral compound, right? And point is that sulfur, again, you could assume 2x, because two atoms of sulfur, and you can each one has an oxidation state of X, you could assume. Then I make it -2 plus 3 times -2, or -2 times 3, because there are 3 oxygen atoms and each one has an oxygen -2. The charge of this complex ion is -2, so I'm going to write this -2. 2x equals to -2 plus 6. X is equals to +4 divided by 2, so that is going to be +2. Again, same answer, just in a slightly different way. So yeah, that's just something to note. Now, question number 9. Ammonia is produced by the Haber process. So this is, the reaction, and a fault in the temperature control during the process results in the temperature changing to 600 degrees Celsius for 2 hours, which is higher than the normal temperature that's used, right? So what does that mean? That if the temperature is higher, that means that the rate of the reaction will obviously be faster, because the temperature causes the rate of the reaction to increase, right? So that means ammonia was formed slower. That's wrong. These two are wrong. Ammonia was formed slower is wrong. Ammonia is definitely formed faster. Okay, the rate definitely increased, but actually, if you see this, delta H equals -92 kilojoules per mole, which implies that the forward reaction is exothermic, because it has a negative enthalpy change, Saturn enthalpy change. And so if this forward reaction is exothermic, the backward reaction is endothermic. But what does that mean? That means if the temperature increases, because exo means that it releases heat, right? So if the temperature increases, and endo means it absorbs the heat. So if temperature increases, then the backward reaction is favored. The endothermic reaction is favored because the temperature has increased, right? So to oppose that change to the system, the mixture will oppose that change by favoring the backward endothermic reaction, and so decreasing the amount of ammonia and increasing the amount of N2 plus 3H2, because what will that result in? The endothermic reaction will absorb the extra heat, right? And so you will re-establish the equilibrium. And therefore, if the temperature increases, the backward reaction is favored, which means that there will be less ammonia, and so the equilibrium yield of ammonia will decrease. Okay, so what does that mean? That means the correct answer is A. All right, now let's go to the next question. For the reaction shown, an equilibrium is established at a temperature of 700 kelvins. The equilibrium constant Kp for the reaction is 9.80 kilopascals. The partial pressure of N2O4 at equilibrium is 80.0 kilopascals. What is the partial pressure of NO2 at equilibrium? Okay, so all of these are in kilopascals actually, so I don't need to convert anything. It's simple. All right, so what we're going to do is first let's write down the expression for Kp. So Kp equals to P square NO2, because I have 2 moles of NO2 gaseous, and then divided by, so that's the product side, and then in the reactant side I have N2O4, so P N2O4. Okay, and now we're going to just substitute the values in. We'll just make some lines to distinguish this. But Kp is 80 point, sorry, no, it's not 80.0, the Kp is 9.80, right? So 9.80 equals to, now NO2, they've not given me the partial pressure of NO2. Let me just take it as X, and because it's P square NO2, I'm going to take this as X squared, okay? And then divided it by the partial pressure of N2O4, which is 80.0. So 80.0. Now just calculate this out. So X squared equals to what? 9.8 times 80, so that is 784. And then now X equals to root of 784. And so that is going to be 28.0 kilopascals. Okay, so your answer for what is the partial pressure of NO2 at equilibrium is going to be 28.0 kilopascals. Okay, so yeah, next question now. The diagram shows the Boltzmann distribution of the energy of gaseous molecules at a particular temperature. Which statement is correct? If the temperature of the gas is raised, the height of the maximum of the curve increases. That is wrong, because the Boltzmann distribution, what happens if the temperature of the gas is raised is that the curve, the peak lowers actually. Like I'm not perfect at drawing it actually, but it flattens and it lowers, and the area under the curve obviously remains the same because it's the total number of molecules, right? But the height of the maximum of the curve, maximum means the peak. This is the peak. The height of the maximum of the curve increases. That's wrong. It actually decreases. As you can see from my diagram, this is for temperature increase. That it just flattens a bit more and the height decreases. Okay. So sorry, why did I put a tick? It's wrong. That's my point. Okay. The second one is that if the temperature of the gas is raised, the maximum of the curve moves to the right. That is true, as I showed you, and that like the curve I drew, the temperature of the gas was raised and the maximum of the curve moved to the right. Can you see this is the right, right? So it moved to the right. So B is right. So I would say B is the correct answer. Now if you look at C, the length of the line labeled X shows the activation energy for the reaction. That is wrong because activation energy is actually on the x-axis. So for example, this would be activation energy. This point on the x-axis would be activation energy. But to say that the length of the line labeled x shows the activation energy is wrong, because what does x represent? X represents something on the y-axis. X represents this height on the, okay, that's not a very good arrow, is it? But x represents this height on the y-axis. And what is the y-axis? The proportion of molecules with the energy E. Activation energy would obviously be on the molecular energy axis, right? So for example, this point, yeah, if I'm assuming it, okay, but a point on the x-axis, but if it's a length on a on the y-axis, that means it's just the proportion of molecules. You know, it's just it represents the number of molecules at this point, and so basically that means that C is wrong. Now, if I look at D, the length of the line labeled Y shows the enthalpy change of the reaction. Of that is wrong, because actually what is Y representing? Y is touching the peak, right? So actually this represents the number of molecules, which is on the y-axis, the number of molecules, the y-axis represents the number of molecules which have the most probable energy. The most probable energy means the energy that is at the peak, that causes the peak, right? So, of this curve. So the number of molecules that have the most probable energy is represented by the length of the line, y. All right. So that is why. So this is wrong. That it shows the enthalpy change of the reaction. No, all energy changes should be represented on the x-axis, and anyways, I don't know exactly how they would show it on the Boltzmann curve, the enthalpy change. But anyways, the point is that D is wrong. So if A, C, and D are wrong, obviously B is right. Okay. Now, next question. Magnesium chloride (MgCl2) and silicon tetrachloride (SiCl4) are separately added to water. What are the approximate pH values of the solutions formed? So magnesium chloride (MgCl2), it's a neutral chloride and it dissolves in water to give a fairly neutral solution, and the pH is around 6.5 and it dissolves in water. So C or D should be right. And SiCl4, it will react with water. So SiCl4 is a liquid, and then it will react with water to give you SiO2, which is a solid, and HCl, 4HCl, right? Which is seen as a white, dense, misty. Uh, it's seen as white, dense, misty fumes, you could say, and it's going to therefore be um acidic. An acidic solution is formed, right? So we can say that the answer should be so A or C would be right in that sense, and so we cancel out these two. So then C would be the answer. Okay, and the next question. Which graph correctly shows the relative melting points of the elements magnesium, aluminium, silicon, and phosphorus plotted against their relative first ionization energies? Okay, so firstly, silicon. Silicon is in group 4, so it exists as a giant structure, right? Group 4 elements exist as giant structures. And so because of that, silicon will have the highest melting point. So in A, C, and D, silicon has the highest melting point, but in B, silicon does not have the highest melting point, so therefore we can cancel out B. Now, the after that, if we compare magnesium, for phosphorus, obviously because it's a non-metal, so it will have the lowest melting point. And then if you compare, which is the case in all four of the diagrams, but then if you compare magnesium and aluminium, so magnesium in its metallic lattice, it will exist as Mg2 plus and it's C of electrons, right? Whereas aluminium, it will exist as Al3 plus and it's C of electrons. So obviously, if aluminium atom has lost each aluminium atom has lost 3 electrons in its metallic lattice to form the metallic bonding, then basically, um, you know, aluminium metal will have a greater sea of electrons, a greater number of electrons in its conduction band, and because of that, is going to have the higher melting point, if you get what I mean, because it has a greater sea of electrons, right? Um, so therefore, aluminium will have a higher melting point than magnesium, which is the case in A. And if you look at B, aluminium does have actually B was wrong because of silicon being lower than aluminium, right? And if you look at C, aluminium is well quite. I mean, I guess it seems to be a bit higher than magnesium, so it's right. And then even in D, so I guess you can't eliminate it outright. Or however, like maybe this one is a very small difference. I don't know. We'll see because I'm still not sure. Then if you look at the first ionization energies, so I'll just write out the period 3 elements: sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. Okay. So across a period, the first ionization energy will increase. And why is that? Because across a period the number of shells remains the same, right? But your number of electrons increases across the period. I mean, really your number of electrons increases, so therefore your number of shielding electrons um, increases, but that's a very slight increase because they are in the same period. But the main factor that, because obviously like I mean to say they have the same number of shells, right? And then the new electron, like this had one, and then this one it will have two. So the new electron is added to the same shell, right? So it's only a bit, not like it's not that big of a increase in the shielding really, because it's still being like the new electrons are being added to the same shell. But the bigger factor that's affecting the ionization energy across a period is that the proton number is increasing, right? So sodium, it has 11 protons, magnesium it will have 12 protons. So obviously if there are 12 protons in the nucleus, there is this greater nuclear force of attraction on the valence electrons, right? I mean, really, the shielding doesn't change that much. It's fairly constant, just to make myself clear, because shielding is caused by the inner electrons, right? Or the inner subshells of electrons. So the shielding is fairly constant, but the proton number is increasing, right? And because of that, the nuclear force of attraction increases, and so the valence shell is pulled closer to the nucleus, and therefore it will take more energy to remove the outermost valence electron from the atom as you go across the period. So the first ionization energies increase across the period. I hope that makes sense. I think I gave a quite a convoluted explanation today, but again, you guys are free to comment if you have any questions. And then basically, then your highest first ionization energy should be for phosphorus, which is the case in all four of them. Then the lower one after phosphorus should be silicon, which is the case for all of them. Then if you compare magnesium and aluminium, that is quite a special situation because magnesium is in group 2 and aluminium is in group 3. So what happens when you go from group 2 to group 3 is that it doesn't actually follow the trend of the first ionization energies increasing across the period, but actually what happens is that if you look at the electronic configuration of magnesium, which has 12 electrons, so 1s2, 2s2, 2p6, 3s2, right? And then as I told you, shielding is caused by the inner shells, but actually it's also like if even the same shell, the lower subshells can shield the higher ones. If you get what I mean. So aluminium, if you look at aluminium, because it has 13 electrons, so 1s2, 2s2, 2p6, 3s2, 3p1. So as you can see, an extra subshell has been added to aluminium. I mean, aluminium has one electron in another subshell, right? So then, because of this additional subshell, 3p, right? So because of that, because it has one electron in that, so because of that aluminium, there is a greater shielding effect in aluminium. Okay, and because actually across the period the shielding doesn't change that much really, not too much because the inner shells remain the same and more electrons get added to the outer shell only, right? But for magnesium versus aluminium, because it's in a different subshell, so I mean to say a new subshell has been added. So because of that, or not added per se, it was already there, but electron got added to the subshell. I say it like that. But anyways, there's greater shielding effect for aluminum, and so because of that greater shielding effect, the nuclear force of attraction on the outermost valence electron, it decreases a bit. So because it decreases, the nuclear force of attraction on the outermost valence electron decreases in aluminium a bit. So it will actually have a lower first ionization energy as compared to magnesium. So it will not follow the trend of the ionization and first ionization energy increasing, but actually from magnesium to aluminium, there's a slight dip in the first ionization energy. So basically, that means that in this x-axis where there's first ionization energy written, aluminium should be before magnesium because aluminium has a lower first ionization energy as compared to magnesium. Okay, so now let's look at A because we already canceled out B, but if you look at A, C, and D, so aluminium is before magnesium in C, but that's not the case in A, and neither is it the case in D, right? So that means that our correct answer must be C because it matches all that we know about melting points and first ionization energies. Okay, so yeah, next question. The table gives information about calcium carbonate and calcium hydroxide. Which row is correct? carbonate is more soluble than calcium hydroxide. Okay, that one must be incorrect. So calcium carbonate is definitely not more soluble than calcium hydroxide. Why is that? Because group 2 carbonates, like all of them are insoluble in water, right? Whereas group 2 hydroxides, you know, if you just take group 2 and a group 2 element is M, okay, consider that. So then the group 2 carbonates, their solubility increases down the group, right? So their solubility increases down the group. But my point is that the group 2 carbonates are all insoluble in water. Whereas for group 2, sorry, not, why did I write MCO3? Sorry, I meant to say group 2 hydroxides. Okay, group 2 hydroxides, their solubility increases down the group. Maybe I should make a downwards arrow, I don't know, but whatever, but increases down the group. Okay, so for hydroxides, group 2 hydroxides, their solubility increases down the group. Whereas group 2 carbonates, they are insoluble in water. So this one, that means our correct answer must be A or B. And then calcium hydroxide can be manufactured using calcium carbonate as a starting material. Let's try to make an equation of that. So calcium carbonate plus H2O perhaps can give you CaOH twice plus what should I say? CO2, is that balanced or not? C and 3, 2, 3, 4. It's not balanced. Let me make this 2 H2O, and then we can make this, or maybe, I mean, we have water already in the reactant side. What we can do is COH twice plus, so CaOH twice, and then we have 2 H. So we can get like H2CO3. Is that balanced? 3, 4, 5, 3, 4, 5, 4, and 2 plus 2 is 4. Yeah, that is balanced. So that could be a possible equation. And here we have calcium carbonate, and that is the starting material. In the end, you get calcium hydroxide. So it certainly is possible. Of course, there could be other possible equations, I suppose, like maybe CaCO3 plus H2O. And I'm using water. Maybe there are other possible um, reactions. I'm not in industry, so I wouldn't know yet. But you could research about it as well. But this could be another possible route, I suppose. I don't know. But CO plus H2O gives you CaOH twice. And so start from C, and then you've got CO plus H2O plus CO2. But the problem here is that I don't know if this would be very probable because you have H2O here as well as H2O here. So doesn't that get cancelled out? So I suppose that's more like thermal decomposition of CaCO3 first. So you don't really need water for that, I suppose. So thermal decomposition of CaCO3, and then you react the CaO with H2O. So I guess that could be another route, or you could react it with water. So you could do the water reaction, or you could do thermal decomposition. Maybe there are other possible things. But my point is that where do I have two ticks? I have two ticks here, so B is going to be the answer. And let's go to the next question. Which row correctly describes the reactions of calcium and strontium with water? All right, so I mean, both of them would react in similar ways. CaO plus H2O gives you CaOH twice plus H2, right? Metal plus water. So then if you write down the group 2 elements, P, Mira, Ka, Sar, Pada. Okay. So then now they're asking substance reduce, substance oxidize, more vigorous reaction. So I mean, we are forming, first we had calcium and then we're forming calcium hydroxide, which obviously has oxygen. So I would say the substance oxidized is calcium or strontium. Because if you look at calcium, that's the pure elemental form, so it has an oxidation state of 0. Whereas in CaOH twice, the O hydroxide ion OH minus, it has a negative charge, -1, and then because there are two of that, so it's 2 OH minus. That means the calcium ion must have a 2 plus charge, so Ca2 plus, right? Which is obviously the likely ion you would get from group 2. but you're going from 0 to 2 plus, so obviously oxidation number is increasing, which means it is obviously oxidation. And if this is becoming oxidized, then obviously water must be getting reduced, so H2O to H2. That is obviously you're losing oxygen, so it's reduction, right? And so your answer is going to be either C or D. And a more vigorous reaction out of calcium and strontium. So down group 2, what happens is, imagine this is calcium, just representation, not actual actually, obviously, but and then there's strontium. So down group 2, what happens is that, like, calcium, if you look at the periodic table, it's in 1, 2, 3, 4, so period 4, right? And strontium is in period 5. So because of that, what is going to happen is that, what that means is calcium has 4 shells, whereas strontium has 5 shells. And because strontium has 5 shells instead of 4, so what difference does that make? That means that the outermost valence electron of strontium, because if, I mean, they're in group 2, so obviously they have 2 electrons in their outermost shell, but the outermost electron of strontium, it is held less tightly to the nucleus. Like, the nuclear force of attraction on it is weaker because strontium has a greater number of shells. And so because of that, the outermost valence electron, because it has less nuclear force of attraction on it compared to the one in calcium. So because of that, strontium is going to lose that valence electron more easily as compared to calcium, and it loses that electron more readily. And so because of that, reactivity increases down group 2. That's the trend down group 2, that reactivity increases of the group 2 metals down the group. And so because of that, the reaction of strontium with water will be more vigorous, because it's a bigger um, it's a bigger atom. So yeah, and so we have 3 ticks in D, so D is going to be the answer. The next question. Chlorine gas is added to cold aqueous sodium hydroxide. In a separate experiment, chlorine gas is added to hot aqueous sodium hydroxide. Which oxidation states of chlorine are found in the reactants and products of the two reactions that take place? Alright, so let's write down the two reactions. So these are actually quite famous case studies in AS, I would say. You should have seen them by now. But this is cold dilute NaOH. Well, they said cold aqueous, but I mean, if you have cold dilute conditions, that's what happens. Aqueous, obviously, they're going to use aqueous NaOH for this reaction, but Cl2 plus NaOH gives you NaCl plus NaClO plus H2O. So that's the reaction. And then obviously to balance it, you put a 2 here because Na and Na. Just check if it's balanced. 2Cl and then 1O here, 1O here. Yeah, it's balanced. Okay, so that's the reaction. And the second one with the hot aqueous sodium hydroxide. So actually, in the book or something, you would have hot concentrated sodium hydroxide written. And then you're gonna get NaCl plus NaClO3 formed. So it's more vigorous, so you get, this compound and H2O. You have to balance it. This is 5 NaCl. You have 3 Cl2, 6 NaOH. Now you could balance this using, redox chemistry and, oxidation states and stuff. But because it's such a famous case study, so I just kind of know it. And there should be 3H2, but let me just confirm if it actually is balanced or not. 3 Cl2, 6, and then that's 1 plus 5, yeah, 6, and then 6 Na, so 5 plus 1, 6, and then 6 all oxygen, so 3 plus 3, yeah, and 3 2s are 6, so hydrogens, yeah, it's balanced as well. Now, what oxidation states of chlorine are found in the reactants and products of the two reactions that take place? So obviously in Cl2, because that's the pure state of chlorine, natural state, so it's going to be 0. Elemental state, as this is going to be 0. But I don't know if I call it elemental, but like this natural thing, right? So anyways, and then NaCl, so obviously it's Na plus Cl minus. So over here you're going to have -1 as the state of chlorine. Again, over here you have -1 because this is also NaCl. Now in NaClO, in the compound NaClO, there are two ways you can do it. One is that, obviously Na, group 1 has a fixed oxidation state of +1. then we don't know chlorine's oxidation state, we're going to take it as X. And then oxygen, it has a fixed oxidation state of -2 usually, and the whole overall compound has an oxidation state of 0. So X equals, so X -2 plus 1 is -1 equals 0, X equals to +1. So that's one way of doing it. The other way is that we have NaClO is basically Na plus ClO minus, right? So this ClO minus ion has a -1 charge, so -1 equals to, because the overall charge is -1. Oxygen, it has a fixed oxidation state of -2, and we don't know the oxidation state of chlorine, so we're going to take it as X equals -1 plus 2, X equals to +1. All right, so that's the other way of doing it, and you get the same answer. The point is that in NaClO, chlorine has an oxidation state of +1, so we found that out. And now we're going to do the same procedure for NaClO3. So here is +1. Now for NaClO3. So again, NaClO3 is basically Na plus ClO3 minus. So I can take this complex ion. So -1 equals to X, because chlorine is, I'm going to take it as X. Now I have 3 oxygen atoms, so I'll make it 3 times -2, because oxygen has a fixed oxidation state of -2. And -1 equals X minus 6, -1 plus 6 equals to X, usually, I mean, and then X equals to +5. So over here, chlorine has an oxidation state of +5, all right? And the other method you could use is you could just overall NaClO3 has no charge, so you could take it as +1 for sodium, then X for chlorine, and then +3, because there are 3 oxygen atoms, times -2, because oxidation state of oxygen is -2, and then equals to 0, because that's the overall charge of the compound. -6 plus 1 is going to be -5 equals to 0. X equals to +5. All right. So again, you got the same answer. Anyways, so let's now check the options. So we got 0, -1, +1, and +5, right? As this oxidation states of chlorine in all these reactions. So 0, -1, +1, that's wrong. Obviously, 0, -1, +1, and +5, that's right. So A would seem to be the answer. 0, -1, +5, wrong. 0, +1, +5, that's also wrong. So A is going to be our answer. And the next question, a test tube of HBr and a separate test tube of HI are heated to the same temperature. Which combination of observations is possible? So we have fluorine, then chlorine, bromine, iodine, and this is a halide compounds of them, right? Sorry, hydrogen halides. I mean to say hydrogen halides. Yeah, that's the proper term, I would suppose. Hydrogen fluoride, hydrogen chloride, hydrogen bromide, hydrogen iodide. Because they're all gases. That's why I'm saying this. Otherwise, if it's an aqueous state, then this would be hydrochloric acid, hydrobromic acid. Because it's gaseous state, so it's hydrogen chloride, hydrogen bromide, etc. And I should not forget about astatine, I suppose. Hydrogen acetate, fluorine, chlorine, hydrogen acetate. Anyways, the point is, okay, so down the group, what happens? Similar to the explanation that was for the group 2 things, I mean to say, if I compare, okay, so we have bromine and iodine here, right? So hydrogen bromide and hydrogen iodide. So bromide, imagine this is bromide, and then iodide is like that, it's bigger. And then you have hydrogen, which has a fixed shape. I don't know if I'm able to draw the same, but assume that this is the same radius of a circle, okay? And so what happens is that because iodine atom is a bigger atom, so because of that there is more um, overlapping between, there's more atomic overlap between hydrogen atom and iodine atom as compared to the hydrogen atom and bromine atom. All right, so because of the greater um, um, orbital overlap, so the bond length is greater, and if the bond length is greater, so bond length is greater, which implies that the bond strength is lower, actually, because the bond length is greater. So a longer bond length means that it is a weaker bond. Okay, so that's just uh, yeah. So basically, because it's a weaker bond, it's more reactive. Okay, and so if I look at the options, firstly, so they're heated to the same temperature, right? So if they're heated to the same temperature, whatever temperature it is, basically it's more likely that HI would react as compared to HBr. So it's very possible that both of them show reactions, HBr and HI. I don't know the temperature actually. If it's a very high temperature, obviously both of them would um, decompose and stuff. But if it's a lower temperature, then depending on what the temperature is, if it's a very low temperature, then neither of them will react. But if it's a reasonable temperature, then HI would react, but HBr might not. So HI will be quicker, hydrogen iodide will be quicker to react because it is a weaker bond between H and I because of the greater size of the iodine atom, which means a longer bond, and because of that, a less strong bond, a weaker bond. Okay, so anyways, let's read the options. Firstly, HBr, so bromine, you can't have a purple vapor for that because purple is the color of iodine vapor. So we can cancel B out immediately. Then for the same reason we can cancel out C because the brown vapor would be characteristic of bromine, but not of in this context, but not of iodine, right? So the vapor, I mean, so and we can cancel out B and C for those reasons. Now, if you look at A versus D, A implies that HI has not reacted because there was no change. HI has not decomposed, I mean, because they're heating it, so this is thermal decomposition that's taking place. So HI has not decomposed, whereas HBr has decomposed because a brown vapor appears of Br2 gas. But that's wrong because, as I told you, Hi is a weaker bond, and so weaker molecule, weaker bond, because of the greater size of iodine atom. So because of that, Hi should react. Like if HBr is reacting, that implies that Hi should have reacted first. And but if they're saying that there's no change, then that has to be wrong. Okay. Whereas if you look at option D, they're saying that HBr had no change, but for Hi, a purple vapor appeared, which is possible, it's plausible. Out of all the options, this is the most plausible one, that HI, a purple vapor appeared. HI decomposed, but HBr, because it's a bit of a stronger bond compared to HI, so because of that, HBr did not decompose that easily at this certain temperature that they've heated both the test tubes to. So I would say that D is the answer. Hope that makes sense. Okay, next question. Ammonia exists as simple covalent molecules NH3. Ammonia can react with suitable reagents to form products containing ammonium ions NH4+. Ammonia can also react with suitable reagents to form products containing amide ions NH2-. Which of these nitrogen-containing species are present in an aqueous solution of ammonia? So an aqueous solution of ammonia means NH3 aqueous. And the thing is that we know that ammonia is a weak base, right? So, technically, so I mean, if you react it with water, what should happen? Let me actually. Okay, sure, we can just write it like this. So NH3 plus H2O, that should give you like NH4 plus OH minus, right? So it's accepted one proton from the water. So one H plus is accepted in an H plus, and it gives you OH minus, which proves its basic nature. So in this case, I mean, obviously, yes, ammonia can give you NH2 minus when it reacts with certain products, but they're talking about an aqueous solution of ammonia. So with water, yeah, it should show its basic nature, right? Its weak basic nature. So I would say that the nitrogen containing species present would be NH3 and NH4 plus, not NH2 minus. So the answer would be um, ammonia molecules and amide ions? No. Ammonia molecules and ammonium ions only? Yes, that's right. So because it's a weak base, so otherwise, there would be, if it was a strong base, there would be complete dissociation and all. But because it's a weak base, I guess I should clarify that as well. There's going to be sort of an equilibrium between NH3 and NH4 plus, like the two sides of the equation. So because of that, there's going to be ammonia molecules and ammonium ions. It's not going to be either or, but actually both of them will be there, but not NH2 minus because ammonia is a weak base, so it's showing its basic nature here. When it's in its reaction with water, and then the reagent is water. Okay, so yeah, and then next question: what would be produced when 60 grams of nitrogen monoxide react with an excess of carbon monoxide in a catalytic converter? So let me write down the equation of what happens in a catalytic converter. So this is going to be N2 plus CO2. Now to balance it, well, either you could balance it by putting a 1 by 2 over here. As just that balance, let me just check. Yeah, it's balanced. Or you could balance it by putting two, two, nothing here, and two here. Another way of balancing it. But actually, I'm gonna go with this. But obviously, you can still just put the half there. That's more convenient, really. Anyways, you have 60 grams of NO. Okay, and then what's the MR of NO? Is just going to be 14.0 plus 16.0, right? So that's like 30 and grams per mole. So then how many moles of NO do you have? So moles equals to M over MR. Obviously, so it's going to be 60 over 30, which is just going to be 2 moles. And actually, that's convenient that I already have 2 over here, so it's just the same ratio. All right, so 2 moles. And now they're asking about carbon dioxide, nitrogen. Okay, so they're asking about all of them. So I suppose I just calculate out the amounts of all of them, really. But carbon, actually, no, wait. They're asking about carbon, but there's an excess of carbon monoxide. So the more likely product, if there's an excess of carbon monoxide, would not be carbon because it's an excess of carbon monoxide. So the more likely product would be carbon dioxide, right? That's the one you've probably learned as well. And so I'm going to cancel out A and B for that reason. And even it says nitrogen dioxide, the more likely product is N2. And so it's either an option of C or D, right? And now we're gonna check. So the ratio between NO and N2 is 2:1. So if this is 2 moles, this should be 1 mole. And the ratio between NO and CO2 is 2:2, which basically means 1:1. So if this is 2 moles, this should also be 2 moles. So I got 2 moles here, so this should also be 2 moles. Okay, now I have to calculate the masses. So MR of N2 is just going to be 14.0 times 2. You can use your product table, by the way. I didn't open it today, but just use it. And then this is going to be 28.0 grams per mole. Then MR of CO2 is just going to be 12 plus 16 plus 16 because there are 2 oxygen atoms. So 12 plus 16 plus 16 is 44. And this is going to be 44. And now you're just going to calculate the mass. So mass equals to the moles times the molar mass. So mass of the nitrogen formed is 1 times 28.0, so that's 28.0 grams, right? So that means C is probably my answer, but let's confirm by checking the mass of carbon dioxide as well. Which is going to be 2 times 44, which is 88.0 grams, right? So that means that yes, C is my correct answer. Okay, now let's go to the next question. Structural isomerism and stereoisomerism should be considered when answering this question. Which formula identifies a single substance? Okay, so we have CH3, CH, CH, Cl, CH2, CH. So let me draw that out. So there's 1, 2, 3. Oh, sorry, 1, 2, 3, 4. So four main carbons in the main chain, and then you have CH3, CH, Cl, and then you have CH2, CHO. So this is an aldehyde. And let's see, does this have any isomers? Well, I think because this carbon, which I shall just highlight or something. Can I highlight it? Okay, this one, yeah. So that carbon, it has one chlorine attached to it, one CH3 attached to it, one CH2 CHO attached to it, and one hydrogen attached to it. It's not drawn in the skeletal formula, but it's there. And so it has 4 different groups attached to it, basically, which means, yes, it will show optical isomerism. And so because of that, because there's an isomer of it, so it doesn't identify a single substance, does it? So we can cancel out A. Then if you look at B, you have 1, 2, 3, 4 carbons in the main chain, so 1, 2, 3, 4, and CH, double bond CH, because, there's one attached to it. So it's going to be this, like the compound looks like this, because this carbon has H attached to it and CH3, and this carbon also has H attached to it and CH3. So there's a double bond between these 2 carbons, basically. Okay. Now, does this compound show isomerism? Yes, it does. If you want, you could also draw it like this if it makes more sense to you. You know, it doesn't matter. I just like drawing skeletal formulas because they look elegant to me. Anyways, the point is that it will show cis trans isomerism because this carbon is attached to H and CH3, so these two are different groups attached, right? And then this carbon is also attached to like two different groups. It's not attached to H and H or CH3 and CH3. No, it's attached to H and CH3. So two different groups. So that means that this compound can show geometrical isomerism, i.e., it can show cis trans isomerism, right? So that means again, this compound represents this the formula that they've shown C H3CH double bond CH, which again also wrote like this. That's the trans form. This is the cis form. But the point is that this does not identify a single substance either. It also identifies an isomer, right? So I mean, it identifies an isomer. So that's B is wrong as well. Now if you look at C, it's one, two, three, four. Sorry, did I do that right? One, two, three. Sorry, one, two, three. Actually do four. I don't know why, even though I said three, but anyways, one, two, three, and then CH2, Cl. So apparently this has a chlorine attached, and then there's CH2 and CH, Cl2. So this terminal carbon has two chlorines as well. All right. So now this is the compound. You could draw it out in a displayed form if you want and stuff. But anyways, the point here. Wait, wait, because said which formula identifies a single substance, right? So technically, like this one, like CH3, CHCl, CH2, CHO, like this is the formula, right? So I've drawn out the formula, and in that formula, like, you can basically, you know, if you have structured isomers, then they have the same molecular formula, but different structure formulae. But if you have, like, I mean to say, if you have stereoisomers, then they have the same molecular formula and structural formula. So this is like a sort of condensed version of a formula, I would say, right? And structural formula, like CH3, CHCl, CH2, CHO. So this structural formula, like it represents two compounds, like because the first one had stereoisomerism, right? So this same structure formula represents two compounds. But then I mean, this is technically a skeletal one, but the structure one represents two compounds. Second one, again, that compound represents two compounds here, right? And then if you look at this one, I mean, technically, if the other compound that I was talking about, because I would say that this is technically an isomer of this one, right? I mean, it is an isomer, but the thing is that they said which formula identifies a single substance, and they've given you like, uh, structural formulas. So because of that, this is not the same formula. This would actually be CH2, Cl, CH, Cl, CH2, Cl, right? So that's a different formula than the one given in C. So maybe that's why C. I think that's the more plausible reason for C being the answer. So it does have an isomer, obviously. I mean, now that I think of it, it was quite obvious. I don't know why I was confused. But yeah, it does have a isomer. But the thing is, they're asking about which formula identifies a single substance, and this formula definitely identifies a single substance because the only isomer I can think of really is this one. I mean, you could obviously also have this one, I suppose, which is like all of them in one one of the terminal, all of the chlorine substituents in one on one of the carbon atoms. So, but again, that would be a different formula, different structure formula. I mean, right? So CH3, CH2, C, um, CH3, CH2, and then this one would just be Cl thrice. Okay, yeah. So let me just see if I've written this right. 2 plus 2 plus 1. So that's probably why C is the answer. I hope that makes sense. That if this specific formula represents just one substance, I mean, you could have isomers obviously, but those would have different structural formulas, formulae, I should say, perhaps. But yeah, and C4H10 on the other hand, C4H10 is just a molecular formula, right? So obviously, this is also C4H10, and this is also C4H10. So that's just different. Even in fact, this would be C4. Wait, would it be? Let me check. Oh, 1, 2, 3, 4, 5. Yeah, that would be different. That's actually C4H8, right? So it's cyclobutane, but that means it's basically a type of alkene, right? So I forgot that. But yeah, anyways, I hope that didn't confuse you guys. All of my Hope my confusions didn't confuse you all, but yeah, basically the answer is going to be C, and I hope that makes sense, all of that. I was confused for quite some time, and I don't know why actually. I suppose it's very important to read questions carefully. Anyways, let's go to the next question. Structural isomerism and stereoisomerism should be considered when answering this question. If a molecule contains two non-identical carbon atoms, four optical isomers exist. Okay, that's quite reasonable. I mean, 2 square is 4, right? So yeah, 2 times 2 is 4. Anyways, how many isomers are there with the molecular formula C7H14O and a 5-membered ring and a tertiary alcohol group, right? So we have all these conditions, and firstly, we know that there is a 5-membered ring. So let me draw like a pentagon-esque shape, a pentagon type shape, and we know that, okay, there is a 5-membered ring firstly, and we know that it has 7 carbon atoms in total, and there's a tertiary alcohol group. So perhaps one of the compounds could be this one. So this OH, this is a tertiary alcohol because this carbon atom that's attached to the OH, it is attached to 3 other carbon atoms, right? So again, it's going to be C7H14O because I mean, if you want, you can confirm by counting, and obviously there's only one oxygen. And how many hydrogens are there? Obviously it's let me just 1, 2, 3, 4, 5. Okay, I missed out one carbon, so let me just add a carbon there. Okay, so now we have 7 carbons, so C7, and H, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Did I count this? Yeah, I did count it wrong because this carbon is already attached to 4, so I can't have another hydrogen. Why am I so confused today? I don't know. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So yeah, 14. Okay. I hope you guys are better counters than me. But anyways, that's one of the isomers. And again, over here, this is a chiral center, this carbon. Why is it a chiral center? Because this is wait. No, I'm wrong. If I actually look at this, so I have an axis of symmetry, don't I? Like this side is identical to this side. I mean, these two groups can rotate obviously because it's just, single bonds, but this is an axis of symmetry that I have over here. And because of that, this cannot be a chiral carbon. So that was not right of me to draw an asterisk. This is just one isomer, okay? So this is just number one, okay? So that doesn't have any isomers. That's one till now, and let's draw some other possibilities, okay? So another possibility could be that I have this carbon, and then I have one like that, an OH, and then on some other carbon I have another branch there, a methyl branch. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So yes, 14, C7H14O. And over here, now it's no longer symmetrical because this is not an axis of symmetry, because here I have methyl on this side but not on not on this side, right? So it's not an axis of symmetry, and neither for the methyl group is there an axis of symmetry, because if I divide it, then over here I have this group, but on this side I don't have the CH3 and the OH, right? So not group, but groups actually. But anyways, point is that there's no axis of symmetry in this molecule. Therefore, this carbon atom is chiral, and this carbon atom is also chiral. And because I have two chiral centers, that means I have four optical isomers, as they've mentioned in the stem of the question, actually. So now, till now, I have 1 plus 4, which is 5. But let's see if there are other possibilities. So I could... Okay, why am I not good at drawing pentagons? I mean, obviously, it's not necessary that it's, instead of pentagon, perhaps more equally sized. I don't know. But anyways, you have... But actually, not equally sized. The point is, I should not wander off. But anyways, I could have the branch, instead of on this carbon, I could have it here. So here I had 1, 2, and now it's 1, 2, 3, third one away from this, and from this side as well, 1, 2, 3. 1, 2, 3. So, in this case, let me think about this. Okay, sorry, I was wrong. Because I was first thinking that there would be an axis of symmetry, but I'm wrong, because if you think about this, so this, I can consider this as carbon 1, and then this would be 2, this would be 3. And from this side, it's 1, 2, 3, 4, right? So it's not an equal distance, obviously, because it's a pentagon. I should have realized that, but and there's one, they're like that. So yeah, but over here, obviously, you had 1, 2, 1, 2, 3, and then 1, 1, 2, 3. So there was an axis of symmetry, but over here, you have no axis of symmetry. So this carbon atom is attached to 4 different groups, basically, and so it's gonna be chiral, and this carbon atom is also attached to 4 different groups, so it's also going to be chiral. And so you have 2 chiral centers, so you're going to have 4 isomers from this, 4 optical isomers from this. And so in total, because I really can't think of any other compound, to be honest, I mean, if you can, that's a good thing, but I mean, to be honest, you can't really, because OH would be here, and then if I had one here, the methyl group here, then that's the same thing, right? So 1, 2, 3, 1, 2, 3. So that's the same thing as this. And if I had why am I drawing some random shape? I don't know. And if I had the methyl group over here, that would be the same thing as this one, because 1, 2, then it's the same thing. So yeah, I can only think of 4 plus 4 plus 1, which is 9 possible isomers, but maybe, if we can find more, well, I don't know, but I can think of 9, so I will say that C is the answer. Okay, our next question. The formulae of 3 compounds are shown: C3H7CHO, which is an aldehyde; C2H5COCH3, which is a ketone; CH2, 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 CH2CH, CH2, CH2OH, which is an alcohol. But from this thing, I would assume it's also having an alkene group, right? Double bond. So, which row shows the correct results? Decolorizes the bromine water. That's obviously going to be the alkane, which I already told you with the last one. So if I draw it out, it's like this: CH2, double bond, CH. Perhaps I shouldn't draw the H like that. But CH, CH2, and CH2 again, and OH. Okay, so that's the displayed formula. And obviously alkenes decolorize bromine water, so it's either going to be C or D then, because we can cancel out A and B, because aldehydes and ketones, they do not decolorize bromine water. Then forms a silver mirror with Toland's reagent. So the compound group that reacts with Toland's reagent is aldehydes. So my aldehyde is the first one, right? C3H7CHO. So that is going to be the one that's right, because it's an aldehyde. Aldehydes react with Toland's reagent. And so my answer, where do I have 2 ticks? I have 2 ticks in D. So D is going to be the answer. Okay. Now the next question. Carboxylic acids may be prepared by several different methods. In which reaction would propanoic acid be formed? The first one is adding ammonium propanoate to dilute sulfuric acid. Should I write it down? So ammonium propanoate, that seems like an ionic compound, I would say. So you have CH3, CH2, COO, but then you don't have that, so COONH3 minus NH3, NH4 plus, sorry, because it's ammonium propanoate, right? And obviously the ion is going to be in that form. So I suppose that would be the compound: CH3, CH2, COO, NH4, or maybe, I don't know, we could write the positive ion first, so it would be NH4. I don't know, man. The point is that this would be the compound, right? Anyways, and you're reacting that with dilute sulfuric acid, so you would get, oh yes, okay, because then you're just sort of protonating it, right? So it's NH4 plus, so CH3, CH2, COOH in that case, and then I suppose you can make this 2 NH4, CH3, CH2, COO. Or maybe it would be better if I put it at the end. I don't know, NH4 and plus, and then this compound, this CH3, CH2, CHO, sorry. I mean, this is a proper no-weight ion, has a negative charge. Okay. Anyways, you get CH3, CH2, COOH. Let me just make it as 2, because I want to balance the equation actually. So yeah, and then you have the compound that you would get is other, like, you got this propanoic acid, which actually they asked me in which reaction would propanoic acid be formed. So I was just actually just the first one, because that's I already got this, but just to be safe, I'll check the other options as well. And then the ionic compound we get is ammonium sulfate, so NH4 twice SO4. Okay, so is that a balanced equation? To me, it seems balanced. Okay, so the propanoate ion just like it just accepted two protons, and then it became propanoic acid. And then the NH4 plus, the two NH4 pluses reacted with SO4 2 minus to form NH4 twice SO4. Okay, that's a reaction. And so I would say A directly is the answer. But let's check the other options as well. Heating ethyl propanoate with aqueous sodium hydroxide. So I have ethyl propanoate. So let me just draw that out. So I have this is the propanoate part. Okay. This is obviously an ester, COO, CH2. Okay, so that's the ester. This is the propanoate part, and this is the ethyl part, right? And so if we're heating it with aqueous sodium hydroxide, that means we're doing base hydrolysis. If we're doing base hydrolysis, that means you're not going to get the carboxylic acid, because the carboxylic acid is obtained by doing um, acid hydrolysis. But if you're doing base hydrolysis, then you're just going to get the the ion. So you're gonna get CH this thing. You're going to get the propanoate ion. You're gonna get it actually because it's sodium hydroxide. So this is obviously going to just form an ionic compound with sodium ion. So it's going to be sodium propanoate basically, right? So you're gonna get sodium propanoate because you're doing base hydrolysis. If you'd done acid hydrolysis, you would get propanoic acid. So that means B is wrong. Then if you look at C, let me just erase this because I need some space. Yeah, and let's look at C. Heating propane tool with potassium manganate 7 under reflux. So you have propane 2-ol. Now acidified potassium manganate 7 under reflux. Okay, so I agree that potassium manganate 7, that is a oxidizing agent. But the problem is that you have propane tool, and they're asking about propanoic acid. Obviously, if you have a secondary alcohol, that is going to be oxidized into a ketone, as you should have learned if you've done organic chemistry. But that's going to be wrong, basically, because to get a carboxylic acid, which is propanoic acid, you would need propane 1-ol, which would then become if you oxidize it, then it becomes propanoic acid. But you have propane 2, which will be oxidized to a ketone. So C will be wrong for that reason. D, heating propyl ethanoate with dilute sulfuric acid. So oh my god, let me draw propyl ethanoate out. I should have just drawn skeletal formulas, but it's okay. Now I've already started, is the problem, yeah. So this is going to be my ethanoate part, and then my propyl part is just going to be this. So now, yeah, now the good thing is, unlike B, they are doing acid hydrolysis because they're using dilute sulfuric acid. But the problem is that they've reversed the compound. It's not ethyl propanoate anymore, it's propyl ethanoate. So you're gonna actually get 1, 2, 3. So you're gonna get propanol, propane 1-ol in fact, and you're gonna get ethanoic acid, right? So you're not gonna get propanoic acid, are you? You're gonna get ethanoic acid, and we need propanoic acid according to the stem of the question. So yes, you'll not get a sodium um, carboxylate, unlike B, but the problem is that you will not get propanoic acid, you'll get ethanoic acid. So for that reason, D is wrong as well, and so your correct answer is going to be A. Hopefully that makes sense. For the next question number 24, the diagram represents the structure of a polymer. By which method might this polymer be made? Okay, so now let's see the methods. A, polymerize ethene followed by hydration. But that's a problem because if I polymerize ethene, then obviously I'll get polyethene, which is basically a long chain alkane, right? So it'll be C, C, H, 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 and then you have continuation bonds, and then it's just repeated n times. It's a long chain alkane. So how do you expect a long chain alkane to just react with water like that, right? It's quite an unreactive substance, polyethylene. So we can cancel out A for that reason. For the same reason, we can cancel out B actually, because you're polymerizing ethene. So again, you get polyethene, which is this compound, and then you oxidize it with cold acidified KMnO4. Now again, an alkane, how will you oxidize an alkane using cold acidified KMnO4? It's not that easy, can it? Is it? So you're going to cancel out B as well. Then if you consider C, polymerize 1,2-dichloroethene followed by hydrolysis. So that's just going to be 1,2-dichloroethene. You're polymerizing that, so you get poly 1,2-dichloroethene, which is this compound, right? And then you just hydrolyze this compound. Now, does that work? Let me think about this. So yes, it does work because you could have like nucleophilic substitution, right? So again with hydrolysis, so hydrolysis with the NaOH aqueous or something, right? So you could do that, and then this would get, these two would get substituted, and so you would end up getting this compound if you do nucleophilic substitution using NaOH aqueous and heat and reflux. So you will get this poly 1,2 uh, dihydroxyethene or whatever its main name is, but yeah, you will get that compound then, right? Not sure exactly what the naming, but that's the compound you would get, which is exactly what you want as well. So I would say that C seems to be the right answer. If you look at D, polymerize 1,2-dichloroethene, which is this compound, followed by oxidation with cholecylfied KMnO4. Now, if you oxidize this, I mean, you're oxidizing this chlorine compound, so that's not really something we've studied. I mean, seems a bit weird, doesn't it? Because I mean, you have OH that's obviously oxidized. Sorry, no, you have Cl. So obviously you can substitute that with OH, nucleophilic substitution. But Cl, can you oxidize that? I mean, it's a bit of a weird statement, really. So I would say that D is wrong, or at least I can't recognize that reaction. So I would say that C is the correct answer. Okay, let's go to the next question. Bromine reacts with ethene in the dark. Which description of the organic intermediate in this reaction is correct? So let us draw out the reaction mechanism. We have ethene. So this is ethene. Then you have bromine, right? And I don't know, I'll just draw bromine like this for now. But basically, it's near this, the double bond is a very, what do you call it? Like it has a very high electron density, right? And because of that, the shared bond pair in Br is bromine nonpolar, so it will get repelled from that high electron density double bond. So it's the double bond is nearer to this bromine, right? And that means further. So the movement will be like this, and so that will therefore, now this nonpolar molecule has become polar, and this will become um, Br minus, and this will become Br plus. Okay, and so in the next step, basically then I mean, I should have drawn this arrow first, I suppose. But anyways, that's what happens with this repel. It got repelled by the high electron density of that. I didn't draw a perfect curly arrow, I suppose, but anyways, it still makes sense, I hope. I'm just not the best at drawing mechanisms, perhaps. Anyways, this goes there, that goes there, and then this becomes CH H H, shall I say, and then CH H. Oh, wait, what did I do? I'm sorry about that. CH, I don't know why I didn't CH. Anyways, CHH, and then this Br becomes, it forms a bond with this carbon, and then you have this bromine. Sorry, actually no, am I doing this right? I think I am. It's been a long time since I've done this mechanism, guys. I'm sorry, I was not really doing chemistry in the past few months because I was busy in some other stuff, and yeah, I suppose that's why I'm a bit doing this video a bit slowly. But anyways, this will be the carbocation intermediate, and then this bromine, it has a full negative charge right now, and this one, it got attached to the carbon, right? And but then this one will like its lone pair will attack this carbocation like this, and then you will get CHHBr. I hope I've not made any mistakes. If I have, kindly tell me in the comments, guys. I would appreciate it. And anyways, that's the mechanism. So um, let's see now. It has a negative charge. So they're talking about the organic intermediate. So the organic intermediate, if I just highlight it, is this one, right? Just the carbocation intermediate. Okay. And so it has a negative charge. No, it's I told it's carbocation intermediate. You can see the plus here. A is wrong. It is a free radical. No, it's not a free radical. Um, doesn't have any like unpaired electron. Anyways, it is a nucleophile. Is it a nucleophile? No, it's not, because it it has a positive charge again, so it wants electrons. So it's not a nucleophile, it's an electrophile. It's an electron lover, an electron seeker, so it wants electrons. It wants a lone pair of electrons. It wants electrons basically. So not necessarily, but yeah, it wants electrons. Yeah, so it's an electrophile. So D would be the correct answer, because it's not it does not have a negative charge. It's not a free radical. It's not a nucleophile. It is an electrophile. So yeah, D is the correct answer. It is in need of electrons. And then if you look at question number 26, I'll just erase this so I have some space. Which statement about butane 1-ol, butane 2-ol, and 2-methyl butane 2-ol is not correct? Okay, so let me just draw them out to make things easier for myself. So this is butane 1-ol. Okay, then I have butane 2-ol, which is this compound, or you could have drawn it as this same thing. Doesn't matter. And then you have 2-methyl butane 2-ol, so that would be like this. And this would be butane 2-ol and 2-methyl, so there would be a methyl branch there. Okay, and then they all react with methanoic acid to form an ester. That's true. That is, and they're asking about not correct. So obviously that's true, because they're all alcohol, so they will react with carboxylic acid to form an ester. They all react with sodium. That is also true, because they all are, again, they have alcohol groups, so they will react with sodium. All of them give you like this compound, and then instead of OH it'll be ONA, yeah, ONA, and then they can all be dehydrated to form an alkene. Again, that is true, because they are all OH compounds. So I mean, this one, uh, if you dehydrated it, would be like this, I suppose. It's 1, 2, 3, 4. Yeah, that's very plausible. Or maybe it would be like that, which is again plausible. 1, 2, 3, 4. Yeah, and then this one, it will be dehydrated to form this alkene. Basically, you lose OH, and this carbon, like the carbon aids into it, you lose the H from that. So, and over here, because you have two adjacent carbons, you could lose either of the two carbons, so you have two alkenes formed. I mean, I didn't really consider stereoisomerism or whatever right now, because I'm not focusing on that, because that's not the focus of the question. So I'm not focusing on that right now. But anyways, you could have, you know, alkenes are able to be formed from all of them, basically, is my point. So C is also right. So then obviously, because A, B, and C are right, so D must be wrong. But if you look at it, they can all be oxidized to a carbonyl compound, which is wrong. Why is it wrong? Because firstly, um I mean, this one, which is butane 1-ol, it is a primary alcohol. So yes, if you oxidize it, it can be oxidized. Like firstly, if you gently oxidize, then it's just going to become this aldehyde, butaldehyde, and then if you oxidize this further, it will become carboxylic acid. But yes, it can be oxidized from an aldehyde compound. And if you look at this one, butane 2-ol, so again, it can be oxidized to give you a ketone, so butanone, right? And further oxidation gives you nothing further, but yeah, that's it. And in this one, 2-methylbutane 2-ol, it cannot be oxidized, because this is the carbon that the OH is attached to. The carbon that the OH is attached to is directly attached to three other carbon atoms, and because it's directly attached to three other carbon atoms, what does that imply? It implies that it's a tertiary alcohol, and tertiary alcohols cannot be further oxidized. Because there's nowhere to really add the oxygen, because you already have like four bonds formed like that. There's no, replaceable hydrogen or anything like that. So, tertiary alcohols cannot be further oxidized. So, statement that they cannot be oxidized to a carbonyl compound is wrong, because this tertiary alcohol cannot be oxidized further, right? So, yeah, that D is wrong. Now, which iodine compound? That's the next question. Will be will react with acidified potassium dichromate 6 and with alkaline aqueous iodine. Okay, so let me see. The first option is CH3CO, CH2, CH3. So if I draw that out, 1, 2, 3, 4. So and then you have a double bond here. So will it react with acidified potassium dichromate 6? No, it will not, because ketones cannot be further oxidized. For the same reason that tertiary, similar reason at least, that tertiary alcohols cannot be oxidized because there's no place to add another oxygen really. So if it does not react with acidified potassium dichromate 6, it immediately fails. These, I don't know, you can't really choose it. So then let's go option B. Option B is CH3CH CH2 CH3. So then just draw that out. That's like this. And now can it react with acidified potassium dichromate 6? Um, yes, it can actually. If it reacts with acidified potassium dichromate 6, which is an oxidizing agent, it can be oxidized into a ketone and then obviously cannot be further oxidized. But yeah, it can react with acidified potassium dichromate 6. So the first thing is a tick. And with alkaline aqueous iodine, yes, it can react because it is a secondary alcohol. This carbon atom that the alcohol OH group is attached to, it is attached directly to two other carbon atoms. So it's a secondary alcohol. And it's a secondary alcohol with an adjacent methyl group, which I'll highlight right now, this methyl group, right? So it's attached to that. So therefore, because it's a secondary alcohol with the adjacent methyl group, it will give a positive iodoform test. Iodoform test is basically, alkaline aqueous iodine, obviously. So yeah, and if it forms some the CHI3, then it's past the iodoform test. So is my point, and that's a yellow substance. So it's called the iodoform test because the substance CHI3 is called iodoform. Okay, anyways, what other thing? Yeah, so basically this also passes the you know it reacts with alkaline aqueous iodine, right? So it passes that test, and so it will react with both of these compounds. Therefore, B is, it seems to be the correct answer. But let's look at the other option as well. If you look at C, CH3, CH2, CH2, CHO, it's 1, 2, 3, 4, and then it's one like that. So will it react with acidified potassium dichromate 6? Yes, it can, because aldehydes can further be oxidized into carboxylic acids. Okay, and can it react with alkaline aqueous iodine? It cannot, because there's no adjacent methyl group, is there? And it's an aldehyde really, but that's why it cannot react with alkaline aqueous iodine. It's an aldehyde and there's no adjacent methyl group either, so it's wrong. And then now if you look at option D, which is again it's a 4-chain substance. So 1, 2, 3, 4, and then it's OH. So obviously this can be oxidized. And firstly, if you just do the gentle oxidation, then it'll be like this aldehyde. But then if you do stronger oxidation or oxidation for a longer time, then it's going to be COOH. So yes, it can be oxidized with potassium, potassium dichromate 6. And then you have alkaline aqueous iodine. Will it pass the iodoform test? No, it will not, because it's a primary alcohol first of all. So this carbon atom the OH is attached to is only attached to one carbon atom directly. So it, am I talking too fast? I don't know. I've gotten those comments in some videos, so I will try to talk a bit slower. I'm sorry, I just don't realize sometimes. Okay, but I'll try. I'm learning through these videos anyways. But this is a primary alcohol and has no adjacent methyl group either. So it cannot react with alkaline aqueous iodine, so it fails the iodoform test. And because of that, B is going to be the correct answer, because A and C and D are all wrong, right? I mean, wrong, comma, right, question mark. That's what I said. Anyways, I don't know. That was a very cringy thing to say, but anyways, B is the answer. Our next question. Chlorogenic acid is found in green coffee beans and is used in treatments for weight loss. What is produced in good yield when chlorogenic acid is treated with an excess of sodium carbonate solution at room temperature? So you have sodium carbonate solution at room temperature, which means that you're not doing base hydrolysis. So it's not base hydrolysis, which means, because it's room temperature. If it was base hydrolysis, it would be reflux. So that means that this COO bond cannot be broken. That means that you cannot have D as the correct answer, because that's showing that this was broken, right? So D is immediately wrong. Then if it's sodium carbonate solution, then that means COOH group will react, because carboxylic acid groups react with sodium carbonate. However, OH does not react with sodium carbonate. Okay. So what will be the correct answer then out of A, B, and C? So in C, COOH has not reacted. In A, you can see that COOH has reacted to give you CONA, and then the OH groups have not reacted. So I would say that A is the correct answer, because in B, if you see, they've shown that the OH group has also reacted with sodium carbonate, which is wrong. Okay, so A is going to be the correct answer. Okay, now let's go to the next question. Butanoic acid can be produced from one bromopropane using reagents X and Y as shown. What could be reagents X and Y? So let me just draw out one bromopropane. This is one bromopropane. Then you're reacting it with substance to give you something, and that something is going to give you butanoic acid. Okay, so this is butanoic acid. Okay, my poorly drawn butanoic acid, but yes. So we had first you had a 3-chain thing, and then you had a 4-chain thing. So obviously you're adding cyanide. And how do you add cyanide? You use KCN or NaCN, which is ethanolic. Okay, and ethanolic NaCN and KCN. And now I mean the C and D are immediately wrong because obviously you have to add one more carbon, which means that your answer is going to be either A or B. Okay, and then you get your it's nucleophilic substitution, right? So Br gets substituted by Cn, and then this is giving you butanoic acid. So that would mean that you are basically doing um, hydrolysis, but you're not doing base hydrolysis because base hydrolysis would have given you butanoate or sodium butanoate to be exact because they've shown you NaOH, right? So base hydrolysis gives you not a carboxylic acid but a carboxylate salt. So I can immediately cancel out B. In D, they're showing oxidation using potassium, sorry, not potassium, but just dichromate that is acidified, but that's wrong as well because it's not really oxidation. I mean, it's hydrolysis, and so that means that A or C would be the correct answer because HCl aqueous is the likely correct option because you're doing acid hydrolysis here. And so I have 2 ticks in A, so A is going to be my correct answer because you added one carbon firstly, and then you hydrolyzed the nitrile group or cyanide nitrile, I suppose more appropriate. I don't know, but anyways, you could say both. I don't know. You could check the syllabus for what term exactly they use. How many esters with the molecular formula C5H10O2 can be made by reacting a primary alcohol with a carboxylic acid? Okay, let's start considering the possibilities. I'll just make the screen a bit big. Yeah. So C5H10O2. So firstly, you could have like methanoic acid reacting with I don't know butanol. So that's 1, 2, 3, 4 butanol and the methanoic acid here. I like drawing chemical formulas. If you wish to write like the displayed formula, or whatever, you can do that. And this is one ester. Can this have any isomers? Let me see. So you could have this is a 1, 2, 3. So you have like a 3-chain one. So 1, 2, 3, and then this could be a branch like that. And then so this is number 1. Then over here, this would not actually be an optical isomer because it has 2 methyl groups attached to this carbon, right? So it has 2 methyl groups attached, so it cannot have any optical isomers, nor can it have cis trans because there's no double bond, C double bond, or anything like that. So then those are the ones possible with methanoic acid. And if I consider ethanoic acid, let me consider ethanoic acid. Okay, so I have ethanoic acid, which means because it's C5H10O2, so if I have ethanoic acid, I should be using propanol as my other compound. 1, 2, 3 propanol. Yes, propanol to be more exact. 1, 2, 3 propanol and ethanoic acid. So that's one more isomer. And then can this have any branches or anything? Actually, that one. Now that I think of it, the compound I drew in number 2, it can also be like this, right? Because if you think about it, now that I think of it, I mean that's one possible isomer where the branch is here, the methyl branch, but I could also have the methyl branch over here. So that would be another possibility. But they said by reacting a primary alcohol, right? So right here, this was a primary alcohol because this O, so OH, it was originally OH, right? The alcohol, basically, the O of the alcohol, it is attached to one carbon atom, which is directly attached to only one other carbon atom. And over here in the second one, this O is attached to one carbon atom, which is directly attached to one other carbon atom, so it's also a primary alcohol. But this one here, the O with, and is attached to one carbon atom, which is directly attached to two carbon atoms. So what does that mean? That means, oh, why did I erase that, man? I'm sorry, guys. I just, that was quite disappointing. But my point remains the same, which is that this carbon atom that the O is OH of OH is attached to, it's directly attached to two other carbon atoms, which means this is a secondary alcohol reacting with methanoic acid, which means that this is not possible. Because I mean, it is possible obviously, but it's not correct according to the stem of the question, because they said by reacting a primary alcohol with a carboxylic acid. Okay, so we're not considering this compound basically. So this is the third one then. And can this have an isomer? Let me see. So you have the same thing and then O, and then I have it like that and this. Okay, so I could have that as well. Um, and but then this one is again this carbon that the OH, the O of OH is attached to two carbon atoms directly. So again, it's not a primary alcohol, it's a secondary alcohol. So this is also wrong. Now, if I consider the methanoic acid one again, which I've written under two, I'll also try one more, which is that if I just have it like this, so 1, 2 here, and then I have a ethane branch. Would that be different? Well, I mean, no, not really, I think, because this is 1, 2, 3, 4, isn't it? And anyways, this one as well, I mean, this carbon that the O of oxygen of, oh, sorry, the hydroxyl group, OH group is attached to, this carbon is also attached to directly to two other carbons. So it's also, again, a secondary alcohol, not a primary one. So I can, that's also wrong. Okay, this is just, oh my god, most of these are not, yeah, never possible with the stem of the question. But anyways, I used ethanoic acid. Now let me use propanoic acid. So this will be propanoic acid, and then O. I'm using propanoic acid, which is three carbons. I have to use ethanol along with that, so I will use ethanol. And then this one is obviously one isomer. And then can I have any other ones? I don't think so, because you can't really have a, yeah, you can't really have a branch there. That's one more. So I have four till now. Then number five, I could, if I used butanoic acid and methanol, right? If I use butanoic acid and methanol, that's number five. Then I could, let me consider if there's a branch of the butanoic acid. So, because there's no, yeah, well, there's no, why did I draw it like that, man? Sorry. One, two, three, four. Yeah. Sorry about that. Is anyways, if I had a branch here in butanoic acid, then obviously the methanol group. So this is also possible. And I don't have any restriction about the carboxylic acid restriction on the alcohol, but this is also a possible isomer then. Okay, so this is possible, and I think that is it. I can't think of any more really. So I will say that there are six possible esters that can be made in this way. Okay, so for using this time of the question. So yeah, and next we have this part. So which statements about the atoms 23, 11 Na and 24 Mg are correct? They're the same number of filled electron orbitals. Well, no, they don't, because I actually written down actually. But anyways, there's the same number of filled electron orbitals. 1s2, 2s, this is for Na. Okay, I'm writing the electronic configuration. 1s2, 2s2, 2p6, 3s1, and then Mg is 1s2, 2s2, 2p6, 3s2. So obviously in sodium, this orbital of 3s is not filled, is it? But in magnesium, it's filled. So magnesium has one more filled electron orbital as compared to sodium. So A is wrong, which directly means that B and C must be right according to the option choices they've given, right? 1, 2, and 3, 1 and 2, 2 and 3. We've already eliminated A, B, and D because 1 is wrong, and so C must be the correct one, which means 2 and 3 are correct. However, I will also test the options, but I can tell you that the answer is going to be C. Okay, they have the same number of neutrons. Yes, they do, because 23 minus 11, that will just be uh 12, right? And then 24 minus 12 is also obviously 12. So they're neutrons. Because proton, the nucleon, the mass number, the nucleon number is the number of nucleons, which means the number of protons plus neutrons in the nucleus, right? So that's 23. And the proton number is 11. 23 minus 11 will be 12. 24 minus 12 will be 12. Okay. So they're the same number of neutrons. They're both reducing agents. Yes, they are, because actually metals are good reducing agents. You know, because if you think about it, like, what usually happens to metals, Na in its lattice, metal lattice, I mean, it will be Na plus, and magnesium in its metallic lattice will be Mg2 plus. So metals usually lose electrons in, that's the standard thing that metals do. really. I mean to say, the type of ions they form are usually cations, is my point. So okay, that means they lose electrons. If they lose electrons, oxidation is lost, right? So they get oxidized basically. Metals are known for being oxidized, and if they are oxidized themselves, that means they reduce other things. So if they are oxidized, that means they are reducing agents. You get my point? So that means that they are both like they're both reducing agents basically. I just kind of prove that, if you get what I mean. And I just showed you in the previous question, the actually no, I'm wrong actually. But anyways, I just showed you this. I meant to say this compound we saw it before, like not this compound maybe. I don't know, but like some nitrile compound anyways. So CH3, CH2, C double triple bond N. So usually if you wanted to reduce this, you would use a substance like LiAlH4 in dry ether. That's what we commonly think of, and then you would get CH3, CH2, CH2, NH2, right? That's what we commonly do. However, another possibility is that instead of LiOH4 in dry ether, you could use sodium in ethanol, because sodium is a very reactive metal, and so it gets oxidized fast, and so it is a very strong reducing agent. So that you don't necessarily need to use LiOH4 in dry ether. In this case, you will use sodium in ethanol. And so my point is that yes, metals are reducing agents usually. So yeah, they're both reducing agents, right? So 2 and 3 are right. So let's see. Okay, now which compounds contain covalent bonds? Aluminium chloride, that is AlCl3. If I just draw it out for you, AlCl, Cl, Cl. So it's just 1, 2, 3, and then 1, 2, 3. Obviously, if you look at aluminium here, it has 1, 2, 3, 4, 5, 6, 6 electrons. So it needs to complete its octet, and because of that, you will find this as Al2Cl6, right? Where there are dative covalent bonds. However, that's not what the question is asking about. But the point is that yes, aluminum chloride is a covalent compound. And then if you look at ammonia, again, ammonia is, a, a covalent compound. So it has that lone pair, and then there are, just write an X actually. So, these are all covalent bonds here. So yes, this ammonia also has, it's covalent bonds. Calcium fluoride, I mean, I think even from the name you might be able to tell that it's an ionic compound, not a covalent molecule. So then it's going to be Ca2 plus and F2 minus that are used to form CaF2. Sorry, not F2 minus. I'm sorry about that. It's 2 of, F minus. So it's CaF2. So Ca2 plus minus and 2 of F minus. So it's an ionic compound, not a covalent compound. And obviously then it doesn't have covalent bonds, does it? So 1 and 2 are right, which means the answer is going to be B. All right. So now let's go to the next question. Ethylene glycol, HOCH2, CH2OH, is used as a de-icer. It allows ice to melt at temperatures below 0 degrees Celsius. That's actually very cool if you think about it. But anyways, I mean, ice melting at temperatures below 0 degrees is very interesting. Okay, anyways, which statements are correct? Ethylene glycol changes the extensive network of hydrogen bonds in ice. Now, if you look at ethylene glycol, CCH, OH, H, H, OH, alright. So, and if you look at water, actually, maybe I should also draw water. H2O, so it's HOH, okay. And it has lone pairs here, obviously. So the thing is that in covalent molecules, when do you have hydrogen bonds? Hydrogen bonds are an intramolecular force, the strongest intramolecular force out of London dispersion forces, or you could call it temporary dipole induced dipole forces, and permanent dipole forces, and hydrogen bonding. So out of these three, the strongest one is hydrogen bonding. And when do you have hydrogen bonding? Well, the five most electronegative elements are fluorine, oxygen, FON, and nitrogen, and then chlorine, and then bromine. And these are the five most electronegative elements. Good to know. And then the three most electronegative elements obviously are fluorine, oxygen, and nitrogen. If you have fluorine, oxygen, and nitrogen bonded to hydrogen, then that in a covalent molecule, then that means you have hydrogen bonding in that compound. So that's and if it's not, if it's an asymmetrical molecule and all that. So, obviously water has lone pairs, so it's asymmetrical, and this will be partially positive, this will be partially negative, and you have oxygen bonded to hydrogen, so it does have hydrogen bonding. Similarly, in ethylene glycol, you have oxygen and hydrogen bonded to each other. and obviously oxygen has the lone pairs again. So yeah, not really a. My point is, this is also this molecule also is not a symmetrical molecule. So this is what do you call it? What was I gonna say? My point is that this also has hydrogen bonding over here and over here. I mean, let's not go into the symmetry, I suppose, better. But anyways, because of that, it can, what can happen is that, if you only had ethylene glycol molecules would form hydrogen bonds with other ethylene glycol molecules. And if you had only water in a beaker or something, then water molecule would form hydrogen bonds with other water molecules and stuff. But because you added ethylene glycol to the ice or to the water, so what can happen is, because both of them have hydrogen bonding, both of them are polar and have hydrogen bonding, so they can, bond, form hydrogen bonds with each other. And so that means that some of the hydrogen bonds that ice has, that water molecules have with other water molecules in ice, some of those can be broken, and then ethylene glycol will form bonds with water in ice, if you get what I mean. So ethylene glycol changes the extensive network of hydrogen bonds in ice. That's right, because both of them had hydrogen bonds, so they're able to form bonds with each other. So yeah, if you get what I mean, is able to dissolve in the ice or whatever. I don't know if dissolving is the appropriate word in this situation, but you get my point. Then second point is that ethylene glycol molecules form hydrogen bonds with other ethylene glycol molecules. I think I mentioned that before, but yes, because it has hydrogen, this one, so it can, if I draw another molecule of ethylene glycol, and I don't know if maybe because I'm not the best at drawing hydrogen bonds actually, but I just draw a lone pair here, and this hydrogen partially positive, partially negative. So this hydrogen over here could form a hydrogen bond with the lone pair on this oxygen, and then this hydrogen over here could form lone pair with this oxygen. Of course, it's not necessary that there are two bonds formed between these two or something, but my point is that this is how it happens, kind of, which should be a bit more linear, so like, whatever. But you get my point, right? So they can, yeah, that's true. Second one is true as well. Now, ethylene glycol molecules will dissolve in the water formed from the ice. Now, obviously, ice is also H2O, and water is also H2O, so both of them have hydrogen bonds, ice and water, because they're the same like molecule, just in a different physical state. Chemically they're the same. So obviously ethylene glycol molecules will dissolve in the water form from the ice. That's also true, because again, this has a hydrogen bond, this has the ability to form hydrogen bonds, and water has the ability to form hydrogen bonds, so they can form hydrogen bonds with each other then as well. So yeah, and so 1, 2, and 3 are all right. Then A is going to be the answer. Hope that makes sense. And now we're going to go to the next question. Carried out two experiments using NO2 as a catalyst to decompose hydrogen peroxide. The equation for this reaction is shown. 2H2O2 gives you 2H2O plus O2. The student's results are recorded in the table. Which statements are correct? The activation energy was the same for both experiments. Well, it should be the same, because it's the same reaction for both experiments, isn't it? Like 2H2O2 gives you 2H2O plus O2. Yeah, so then if it's the same reaction, it probably should be the same activation energy, and then obviously using the same catalyst as well. So the amount that the activation energy is lowered by would be same or similar. So I would say that the activation energy was the same for both experiments is right, because it's the same catalyst, same reaction. And then they're asking the catalyst, the constant, and it's the same mass of the catalyst as well. So yeah, the concentration of the hydrogen peroxide solution was used was 4.0 moles per cubic decimeter. Let me just check. So as sorry, C equals N by V, and the moles are um, well, they've not given you the moles actually. So let me use the volume of oxygen that they're giving you. So oxygen is 490 cubic centimeters, and then that means N of moles of oxygen, because it's a gas, so V over 24, and then that's going to be 480. Now to convert cubic centimeters to cubic decimeters by multiplying by 10 to the power minus 3, or you could think of it as dividing 480 by 1000, and then divide this by 24. That's in decimeters cubed already. So let me just find my calculator. Okay, here it is. So 480 into 10 to the power negative 3 over 24. So that's going to be 0.02 moles of oxygen. The ratio between oxygen and hydrogen peroxide is 1 is to 2. So if this is 0.02 moles, then hydrogen peroxide should be 0.04 moles. And then the concentration of H2O2 will be C equals to N by V. So that's going to be 0.04 divided by the volume, which is 10.0 cubic centimeters. So 10.0 divided by 1000 or multiplied by 10 to the power of negative 3. So that's going to be answer over 10 over 1000. Maybe 4. Yeah, I got 4.0 moles per cubic decimeters. So it seems that 2 is also right. Right. Now, the MnO2 used in experiment 1 was in larger pieces than the MnO2 used in experiment 2. Okay, 0.5 grams, room conditions, 10, 480. The only difference is the time taken, right? So obviously then I guess the thing that we could think is that if this is taking a longer time, then there must have been less. Yeah, it's very possible that there was less surface area of the catalyst available to react. So the MnO2 used in experiment 1 was a larger pieces. Oh, they're saying the opposite thing. It should actually be this, and then to use in experiment 2 than larger pieces than experiment 1, because if it was larger pieces, then it's less surface area, so it reacts slower, right? More time taken. So actually, it should be the opposite statement. So that means 3 is wrong. So if 1 and 2 only are right, then the answer is going to be B. Okay. So why is my screen black? Okay, now it's fine. So yeah, that will be the answer. And now we shall go to the next question. The formula of a solid magnesium compound is MgNO3 twice dot 6H2O when the solid compound is heated in a hard glass test tube. One or more changes are observed. Which statements are correct? Strong heating produces a basic residue. Okay, so let me just write down the reactions. The reaction that occurs. So MgNO3 twice dot 6H2O. Upon gentle heating, all that will happen is that you have MgNO3 twice plus 6H2O, so you lose the water of crystallization. Gentle heating produces colorless droplets of liquid on the upper part of the tissue. That's true, that's water. And then if you do stronger heating, then this MgNO3 twice that you had, it will decompose and give you MgO plus NO2, so 2NO2 plus O2. Now let me check if it's balanced. 4, 5, 6, 7. That is not balanced. Let me just make this 1 by 2 O2. Okay. Now it's balanced. And so strong heating produces a brown gas. That's true. NO2 is a brown gas. And strong heating produces a basic residue. That's true. Because MgO is a basic compound. So that's true as well. So 1, 2, and 3 are all right. So that means that your answer is going to be A. Okay? Let's go to the next question. Sulfur dioxide is an atmospheric pollutant. What might result from the release of sulfur dioxide gas into the atmosphere? All right, so what could happen is, okay, so reduction of NO2 to NO, I suppose so, because if you have SO2, then SO2 will react with NO2 to give you SO3 plus NO, but then NO2 and NO are, what do you call it? They're like acting as a catalyst in this reaction in the atmosphere. Then the NO will again react with half O2 to give you NO2. So as you can see, it's acting as a catalyst because if you add these reactions, then your NO gets cancelled because on both sides, NO2 gets cancelled because on both sides. So you get overall the reaction is SO2 plus half O2 gives you SO3, right? So that happens. So reduction of NO2 to NO, that's right, because you can see it happening, like NO2 is losing oxygen to give you NO, and this the reaction that occurs. That's right. Depletion of aquatic life, that's also true. How? Because this SO3 that's formed, it reacts to the water, and what happens then in water in the atmosphere, and so it becomes H2SO4. And what is H2SO4? H2SO4 is acid rain, right? So then what happens? Acid rain just kind of falls in the rivers and in the places where there is aquatic life, and then obviously because it's acid rain, it will harm the aquatic life in some way. So that is also true. There's water pollution caused, and corrosion of limestone statues, again, that is what acid rain can do because it can react with the calcium carbonate in the statues. I think so that the statues are calcium carbonate, it becomes CaSO4 plus H2O plus CO2 SO4. I mean, I don't know if this is the exact reaction that occurs, but my point is that there will be reactions when it is corroding those statues, right? So yeah, that means 3 is also right. And then if 1, 2, and 3 are all right, then the answer is going to be A. Okay. Now next, which mechanisms are represented in this sequence of reactions? CH3, CH2, CH3 gives you CH3, CH2, CH2Cl, CH3, CH2, CH2OH. Okay, so this first one, it seems to be free radical substitution because you have an alkane that is forming a haloalkane or an alkyl halide. So that is free radical substitution. That's number three. So number three is correct because I can see that. And then if you go to the second thing that's happening, that is just let me think about this. So Cl going to OH, right? So that's nucleophilic substitution. So then two is also right. And then the third one, technically you were so CH3, CH2, CH2, OH is an alcohol going to an alkene, CH3, CH double bond, CH2. So that seems to me, I mean, basically dehydration of an alkene. So it's elimination of water. So what would I call it? Would I call it like nucleophilic elimination? I mean, I'm not sure if that's the correct name of the mechanism, but my point is that well, that's not even an option, so I can't really say that, but it's not one of these. But anyways, CH2, CH double bond CH2 gives you CH3, CH, Br, CH2, Br. So alkenes always give electrophilic addition reactions, right? So this must be electrophilic addition. So I would say that one is also correct then. And so 1, 2, and 3 are all right, and A is the answer. Now, which molecules on heating with ethanolic NaOH means that these are all bromo compounds. So, probably you're doing elimination. Okay, so then produce more than one product with formula C4H8. So ethanolic NaOH implies that there's an elimination reaction here. So then you have bromobutane. So let me draw that out somewhere here. I'll draw it butane and then 2-bromobutane. So you're doing an elimination reaction. So you could form actually two compounds. If you will eliminate the bromine and you could lose H from here, or you could lose H from here to form HBr. And that would give you, or would I form HBr? Or would I form, actually no, because if not like any rush, I'd form NABr and H2. I think that's more likely if I'm not wrong. But again, if I'm wrong, you can correct me in the comments. But anyways, the main like organic product that's formed is of more relevance to the specific question, which would be firstly this one, and then this one, and then the second one that I've drawn. It can have a cis version as well because this compound will show cis trans because this carbon atom is attached to two different groups. This carbon atom is attached to two different groups, right? And obviously there's a double bond as well, so they're going to be cis trans isomerism. So yeah, so that's trans and this is cis, and then this is the compound. So we have this is true that this forms more than one product of the molecular formula C4H. All of these are C4H8. And then if you look at the second one, which is 2-bromo 2-methyl propane. So yeah, also propane. Propane is the main chain. And then you have 2-methyl and you have 2-bromo, right? So if you lose H and you lose Br from this, you're going to get uh, this compound, which would be the same in either direction actually. So yeah, but then this will not show any isomers because you cannot have cis trans because this carbon atom of the CC double bond is attached to two methyl groups. It's attached to two of the same group, and then this carbon atom is attached to two hydrogen atoms. So that means there cannot be a geometrical isomerism. So this one only forms one compound with the molecular formula C4H8. So that's wrong. And then if you look at obviously if 2 is wrong, 3 must be wrong as well. So D must be the answer because only 1 is right. But considering the options that they give, I mean these ones. But I can test D as well. Sorry, 3 as well just to make sure. So it's 2-methyl, right? 2-methyl and 1-bromo this time. 1-bromo. Or you could draw it as this like this as well. It's fine, not a problem. And now if you lose the bromine and you lose the adjacent carbon's hydrogen, then you will get the compound as this one again, the same one, which cannot have cis trans or anything, any other isomers. So then that is it. So this cannot form any more products as well. I mean, so the only answer would be D, one, right? So I hope that makes sense. Next, substance M is refluxed with aqueous sodium hydroxide. One of the products of this reaction reacts with alkaline aqueous iodine to give a pale yellow precipitate, which is the iodoform test. You get pale yellow precipitate as a CHI3. Now, which compounds could be substance M? So substance M. Let me test which of these. So CH3COO CH3, CH3COO CH3. Hmm. Okay, so if I react this, firstly I reflux it with aqueous sodium hydroxide. So that's base hydrolysis, right? And then I get this compound, which is COO minus Na plus, right? So it's the salt. So it's like sodium ethanoate, and then I also get um this thing OH, right? So it's methanol. Now methanol, because they said one of the products of the reacts with alkaline aqueous iodine to give a periodic precipitate, that will obviously be, it cannot be the carboxylate salt, that will be the alcohol if it does react. But then if I react methanol with alkaline aqueous iodine, it cannot give you a positive iodoform test. It will not give you a pale yellow precipitate because it's not a secondary alcohol, it's just a primary alcohol and it has no adjacent methyl group. So then one must be wrong. Okay, if I look at 2, I have CH3COO, CH2CH3. Okay, that's the compound. Now if I reflux this with NaOH firstly, I get what do I get? I get uh, this compound firstly, which is again sodium ethanoate, and I also get, oh wait, I drew it wrong. I'm so sorry about that. Okay, COO, CH2CH3. Okay, then I also get ethanol. Now, actually, the thing about ethanol is that it does actually give you a positive iodoform test. So it's the only primary alcohol that gives a positive iodoform test. No other primary alcohol gives positive iodoform test. Obviously, if you have a secondary alcohol with an adjacent methyl group, it can give you a positive iodoform test, but not any other primary alcohol except for ethanol. So ethanol, why it gives a positive, primary, क्या बोलते हैं? Why it gives a positive test for the iodoform test is because this carbon is basically attached to a methyl group and then there's this OH. So it can give you a positive iodoform test. It's the only primary alcohol to give you a positive iodoform test. So then basically it could be substance M could be um, this compound CH3COO, CH2CH3 because you did get ethanol from it and ethanol will give you a positive iodoform test. Now, if you look at HCOOCH3 twice, so that, let me just draw that out. So that's firstly this part, and then you have CH, which is attached to why is my light flickering? Okay, so two methyl groups. Okay, and then if I reflux this with NaOH aqueous, I will get um, this sodium methanoate, and I will also get from this part, I will get um, this compound, which is a secondary alcohol. Look at that. So I get propane 2, and this is a secondary alcohol, right? And obviously, propane 2 will have an adjacent methyl group. In fact, it has two adjacent methyl groups. So you could consider this one or this one. You could consider either of them. And so because it's a secondary alcohol with adjacent methyl group, so therefore it will give you a positive iodoform test. Obviously, there are other compounds that give positive iodoform tests as well, such as mainly secondary, as mainly like ketones that have methyl ketones, basically ketones that have an adjacent methyl group. So yeah, um, and then you see 2 and 3 are right, which means that C is going to be the correct answer here. Okay. Now let's look at question number 40, and I hope that made sense, all of that. But now, propanol will react with hydrogen cyanide to form 2-hydroxybutane nitrile. The suitable catalyst for this reaction is sodium cyanide. Now, which statements about this reaction of propanol with hydrogen cyanide are correct? So they're talking about mainly the mechanism, I feel. So I'll just draw out the mechanism. Okay, so we have CH3, CH2, then you have COH, right, CHO, and you have a cyanide ion, and this is partially positive is carbon, and then this is oxygen is partially negative. So this one is nucleophilic addition, right? So this goes here, that's the carbon, partially positive carbon, and then this double bond, it breaks temporarily, so then it becomes CH3, CH2, CO, it gets a negative charge because the double bond broke, and then the two electrons from here went to the oxygen. So it gets a negative charge, a full negative charge now, instead of that partial one. But and then you this one, it is now the cyanide is or the nitrile group is bonded here, and then you have H over here, and then from and you had HCN there as well, right? The cyanide, you could consider it to be from, I suppose, NaCN or HCN. Basically, it's NaCN is a catalyst, right? Because as you will see in the mechanism, cyanide or actually the nitrile. I mean, both the names are valid, I suppose, but yeah, it gets regenerated by the end of the mechanism. And this is partially positive, this is partially negative. I mean, this electron, this lone pair is donated to the proton here, the H, and then what happens is then this bond breaks. I mean, these two electrons, they go to the cyanide, it gets a full negative charge after this. And so then what you get is that this lone pair has been donated to the protons, the proton accepts it. And what happens is, I mean, this is, using the Lewis acid-base theory, obviously in CIE A-level course, you study the Bronsted-Lowry acid-base theory, but then the Lewis one is more inclusive than the broader definition of acids and bases. So yeah. Anyways, that this is the compound you get, and along with that, because of this bond broke and the two electrons went there, so you get plus the cyanide ion, right? So yeah, the point is that the cyanide ion, it's and like it got regenerated by the end of the reaction. So NaCN here is acting as a catalyst. Is my point. Okay, so that's just a mechanism roughly. And the cyanide ion or nitrile ion, you could call it either. I think the syllabus uses nitrile, but I'm not exactly sure. You could check in the syllabus. Okay. For 9701, the cyanide ion or nitrile ion attacks the propanol molecule to form an intermediate ion. Now, it is attacking the propanol molecule to form an intermediate ion, as you can see. So that is true. The product of the reaction has a chiral carbon atom. Let me check. This is the product. I will highlight it so you can see it more clearly. Does it have a chiral carbon atom? Well, obviously CH3, this is not a chiral carbon atom because it has H3. This one has H2, so it's also not chiral. This one, on the other hand, this carbon that I'm circling, it has CH2 CH2 attached to it, and it has CN attached to it, and it has OH attached to it, and it has H attached to it. So it has 4 different groups attached to it, so it does seem to be chiral. I will say that this one is a chiral carbon atom. Yeah, the product does have a chiral carbon atom. I'll make that's right. The third thing is that the nitrile ion or the cyanide ion is a stronger electrophile than the HCl molecule. Now that's weird because well, I mean, why do you think electrophile? It should be a nucleophile because this is nucleophilic addition that we're talking about. Firstly, I mean, cyanide, it has a negative charge. It's got a lone pair of electrons. Everything points to the fact that cyanide is a nucleophile, and obviously then HCl is a nucleophile, but it's just a weaker nucleophile, right? So to say that the cyanide ion is a stronger electrophile than the HCl molecule, the statement itself is wrong. So I'm just going to cancel that out. So only 1 and 2 are right, which means that the correct answer will therefore be B. All right. And so yeah, now we are done with this paper. It was a nice paper, quite like like the questions had quite a lot of working, I would say. But anyways, it was a nice paper. So I hope you guys benefited from that, and have a nice day. Thank you.